Welcome to this explainer for the Durga Analytics Premium track. I'm thrilled to be your guide today. As someone with decades of experience building and implementing energy and commodity trading systems, I can tell you firsthand that the absolute foundation of any successful trading business isn't just the traders, it's the data model sitting right underneath them. A single, poorly designed data model can literally hide millions of dollars in exposure. I've unfortunately seen it happen. So in this program, ETRM Data Engineering and Analytics, we're going to build a modern data engineering foundation on a complete, real ETRM trading platform. We're going to learn exactly why an ETRM platform needs one and only one undisputed data model to actually function effectively. Okay, so here's our roadmap for today. We'll start with a quick course orientation, then unpack the 4 fundamental trading questions. From there, we'll dive into the canonical core principle, map out the trade lifecycle, learn how to properly derive downstream metrics, and finally, finish up with your desk-ready key takeaways. Let's kick things off with a quick course orientation to set the stage. Our complete ETRM Data Engineering and Analytics program is a really comprehensive 12-module journey. It's actually the only program out there that teaches modern data engineering on a real ETRM trading platform, going from the canonical trade model all the way to a signed-off P&L built entirely end-to-end by you. The course is organized into 12 modules: data modeling for ETRM systems, reference and master data management, trade lifecycle and instrument modeling, FPML and trade representation, market data, curves and time series, position and P&L data models, counterparty credit and limit modeling, data lake, warehouse and lakehouse, event sourcing and audit trail design, streaming and real-time risk, real-time dashboards and analytics, and finally, straight-through processing as our capstone. Today, we're diving into Chapter 1, which is data modeling for ETRM systems. We are laying the absolute groundwork right here. Every single subsequent module completely relies on the core principles we're about to establish. Now, an ETRM system is a massive, multifaceted beast. Whether you're an architect mapping out the enterprise blueprints, an engineer building the physical pipelines, a business analyst, or a risk manager tracking exposure on a physical crude oil desk, this platform model exists to serve all of you from one single source of truth. You might have entirely different titles and different daily responsibilities, sure, but you all share the exact same goal: getting numbers that you can trust with absolute certainty. So let's step away from the theory for a second and walk right onto the trading floor to look at the 4 trading questions. Picture this. You walk onto a bustling natural gas or power trading desk. The phones are ringing off the hook, prices are flashing red and green on the screens, and the chaos is just palpable. But if you look beneath all that noise, the core function of the desk boils down to a few fundamental concerns. Every single decision a trader makes, whether they're betting millions on LNG cargoes or hedging agricultural commodities, leans on the answers to one precise question: what do we actually need to know right now? Well, here are the answers. First, what's my position? Simply put, how many megawatt hours of power or barrels of crude do I actually own at this very second? Second, what is my mark-to-market, or MTM? If I struck that exact position against today's forward curve, what's it worth? Third, how much money did I make today, and why? That's your profit and loss, and the why is your attribution. Did prices go up, or did we just buy more volume? And fourth, how exposed are we to each counterparty against the credit limit? Now, a naive engineer might look at these 4 distinct questions and think, okay, I'll build 4 separate, isolated systems to answer them. But in a real enterprise, doing that inevitably leads to multiple, conflicting truths on the desk. Your position system says you have 10,000 barrels, but your credit system says you have 12,000. That right there is how millions of dollars vanish into thin air, and exactly how risk managers lose their hair right before that classic Friday afternoon P&L reconciliation panic. To prevent those catastrophic reconciliation breaks, we have to squash that naive instinct immediately. And that brings us to the most crucial concept in this entire explainer: the canonical core principle.
The big takeaway here is that you absolutely must model for every role from one source of truth. Think about it. If you build 5 subsystems with 5 separate copies of a trade, you haven't built a system, you've created 5 competing truths. But if you have one canonical trade record with 5 different views, you have one truth seen 5 ways. This enterprise principle is the secret sauce to ensuring that the trade record the position engine reads is the exact same record the credit engine reads and the exact same record the settlement engine reads.
Honestly, if you remember only one single thing from this entire module, let it be this core idea. Store facts once and derive everything downstream. Your position, your P&L, your exposure reports, they should all simply be SQL queries or calculations running dynamically over a single canonical core of trades. They should never, ever be independently maintained data copies. This right here is the philosophical core of our entire data architecture. Derivation over duplication is what keeps the model right and ultimately what keeps the business safe. Let's move on and see how this builds out in the real world by modeling the trade life cycle. Keep in mind, a trade is not some static, unchanging object. Imagine a physical natural gas trade. It starts out at capture when the trader executes the deal. Then it moves over to confirm with the back office. But wait, the pipeline volume changes, so now it enters an amend state. Maybe it gets canceled entirely later on, or perhaps it moves to novate before eventually reaching settle. A trade is a single, evolving fact that many different subsystems read and annotate as it moves through these states. If you have copies of this trade scattered all across different databases, keeping all those copies perfectly synchronized through every single amendment and cancellation, that is an absolute nightmare.
Let's look at one specific state that trips up a ton of data models: novation. Novation sounds like a scary finance word, but it really just means the counterparty on a trade changed mid-flight. For example, say you're selling power to Company A, but Company A just sold their obligations to Company B. Your canonical model has to remember who the counterparty was historically and who it became. You cannot simply overwrite that database row with the new counterparty. If you do, your past credit exposure reports and your audit trails will instantly break. You need an append-only, bitemporal approach to history, meaning your database has to track both when the business event actually happened out in the real world and exactly when your system recorded it internally.
Now that we understand the life cycle of that canonical core, let's look at the technical proof. We're moving into deriving downstream metrics to see exactly how we turn this trade into actionable numbers for the desk. This right here is where we separate the novices from the senior ETRM data professionals. A stored position table is an absolute anti-pattern. If you physically store your net position in a dedicated database table and try to update it every single time a trade happens, you're just creating a second copy of the truth. And guess what? It will inevitably drift. Trades get backdated, amendments are missed, and suddenly your position table just doesn't match your trade table at all. The best practice is the derived position view. Your net quantity is calculated on the fly as a SQL query, aggregating the buy and sell quantities directly from that canonical trade core. Bottom line, if you store the position as a separate row, you're building a reconciliation break just waiting to happen. And here is the actual math and engineering logic behind that warning. If you do have a stored position table and you run a full outer join, comparing it to a dynamically derived position view based on your trades, any row that returns a difference is a break. But once you completely drop the stored position table and rely solely on the derived view, it becomes mathematically impossible by construction for your downstream dashboards to disagree with your core trade record. You literally eliminate the possibility of a break entirely. So how do we actually build those dashboard numbers? It's all just cascading derivations. First, position is just the net quantity of trades per book and instrument. Easy enough, right? Second, mark-to-market is simply taking that dynamically derived position and joining it to today's market price curve. And third, your daily P&L is just taking today's mark, subtracting yesterday's mark, and multiplying it by your net quantity.
Just 3 short queries can completely reproduce 3 critical dashboard tiles. This proves that downstream metrics aren't these massive, complex data silos. They're just elegant SQL derivations built off a single canonical core. We have covered a tremendous amount of ground today, from high-level theory all the way down to SQL logic. So let's wrap up by evaluating what you really need to take away to be truly desk-ready in an enterprise environment. By mastering this chapter, you're accomplishing a few massive things. You now know exactly how to design a canonical trade table using proper keys and precise data types. You know how to wire up the relationships for counterparties and instruments. And most importantly, you know how to build a derived position view that aggregates quantity as a query, never as a stored row. This right here is the absolute bedrock of the entire trading platform. To truly cement this in your mind, you should be able to draw this canonical core from memory. You need to intimately understand the difference between surrogate keys, meaning those meaningless system IDs, and business keys, like the actual trade ticket number, so your databases scale properly. You absolutely must be prepared to defend why position must be a derived view when someone inevitably suggests taking a shortcut. And you have to instantly recognize anti-patterns, like overriding history. Remember, a senior ETRM data professional is measured not just by the code they write, but by the reconciliation breaks that never happen, because they design the model right from day one. I want to leave you with this final, provocative thought. Can you defend the canonical model like an enterprise architect and trace any number on a trader's screen through its lineage, all the way back to a single source of truth? Keep that question top of mind as we transition out of this foundational theory. You've mastered the single trade model, so get ready to dive right into Chapter 2, where we'll be tackling reference and master data management. Thank you so much for joining me, and I can't wait to guide you through the rest of this journey.
Welcome back to the ETRM Data Engineering and Analytics program. I'm your trainer from Durga Analytics, and I am absolutely thrilled to guide you through this explainer. Today, we're taking a massive step forward. We're going to take the chaotic, incredibly fast-paced physical reality of a commodity trading desk and translate it into precise database mechanics. We are literally turning real-world business into a data model. Just as a quick reminder of where we are in our journey, this is the only program that teaches modern data engineering on a complete, real ETRM trading platform, where you build everything end-to-end, from a canonical trade model all the way to a signed-off P&L. We're currently in Module 1, which is all about data modeling, and this is Chapter 2. In Chapter 1, we established that you have to store a trade once and derive everything else. Right here, right now, we're laying down the foundational vocabulary, entities, attributes, and relationships that's going to support our entire trade lifecycle, market data, and risk valuation moving forward. Here's our roadmap for this explainer. We're going to cover the ETRM foundation, how to distinguish entities from attributes, a real-world disaster called the disappearing barrels incident, attributes and identity, database constraints, and then we'll wrap it all up with some key takeaways. Let's dive in. Starting off with Section 1, the ETRM Foundation. Let's establish the absolute business ground truth before we even think about writing a single line of SQL. Okay, forget the database for a second. Picture a bustling commodity trading desk. It's just a room full of people agreeing to buy and sell things, right? Maybe it's physical barrels of crude oil, cargoes of liquefied natural gas, megawatt hours of power. Or maybe it's financial contracts based on those commodities. At its absolute core, this entire business is just tracking a few fundamental facts. Who traded what, how much, at what price, with whom, and where it was booked. When a trader shouts out a deal or clicks execute on a screen, those facts are instantly fixed. And the people, the locations, the objects involved in these deals, they recur constantly. Which brings us to Section 2. Entities versus attributes. When you start listing out all the things a desk actually cares about, your very first major task as a data engineer or architect is telling the actual things apart from their descriptions. This right here is the foundational distinction of data modeling. An entity is something you can point at, something that has an independent existence. You can literally count them. A trade is an entity, an instrument is an entity, a counterparty like, say, Mercuria or a trading book, those are entities. An attribute, on the other hand, is just a fact that belongs to an owner. It has zero independent existence. Think about it. A quantity is always the quantity of a trade. A price is always the price of a specific deal. Getting this distinction wrong is exactly where ETRM schemas go totally off the rails before a single table is even created. And that leads us to the golden rule of enterprise architecture. You have to decide which nouns get their own dedicated tables versus which ones are just details floating on a trade capture screen. If you find yourself wanting to store the exact same value once and reference it from multiple places, it's probably an entity. If it only ever describes one specific owner, it's an attribute. Let me be clear. If you fail to separate these properly, your aggregations, your position reports, and your risk analytics will absolutely silently lie to you.
So what happens when you get this wrong? Well, let's look at Section 3, the disappearing barrels incident. This is a classic real-world physical delivery nightmare.
Imagine a desk trading WTI crude oil. The physical delivery location is Cushing, Oklahoma. But a developer modeled the delivery location as a free text attribute instead of a referenced entity. So what happens in the real world? One trader types Cushing, another types Cushing OK, and a third types Cushing with a lowercase c. When the risk analyst runs a position by location report at the end of the day, that single physical delivery hub splits into 3 distinct group by values. The desk's risk exposure at Cushing looks like a third of its actual size. They have massive concentration risk, and the system is completely blinding them to it. The fix here is simple. Delivery location must be a referenced entity with a stable ID like location ID 142. Shared reference things are always entities, never free text.
Okay, moving right along to Section 4, attributes and identity. Once we've avoided the disappearing barrels trap, we have to really lock down an entity's specific identity.
When you look at a trade, let's say a crude oil trade labeled BLK 88021, you have to ask yourself, what makes 2 rows the exact same thing? What gives this record its unique identity in the business, and which of these fields belong uniquely to it versus pointing off somewhere else? If you really think about it, a trader's capture screen is just an entity with its relationships made visible to the user. The plain fields, like quantity, price, and trade date, those are the trade's own attributes. They belong solely to trade BLK 8821. But other fields on that screen, like the instrument, the counterparty, and the portfolio book, those are actually references pointing to other independent entities. A trade shares a counterparty with hundreds, maybe thousands of other trades. Recognizing this boundary between a trade's own attributes and its references to other entities is exactly how you build a clean, normalized ETRM system.
Let's look at Section 5, relationships and database constraints. Because identifying entities is really only half the battle. How these entities relate to each other dictates whether your system can actually protect your business reality.
Let's look at the core relationships that define our trading domain. A trading book holds many trades. One single trade generates many financial cash flows over its lifespan. And a single trade can relate to many regulatory risk factors, while a single risk factor obviously applies to many trades. This concept right here is called cardinality, how many relate to how many. It is the absolute core of your referential integrity.
And listen, enterprise cardinality isn't just nice decoration for your diagrams. It translates mechanically into your database structure. Every one-to-many relationship mechanically becomes a foreign key on the many side. So a cash flow carries its parent trade's ID. Meanwhile, many-to-many relationships, they cannot be a foreign key on either side. They absolutely require a third table, an associative or junction table that securely holds those pairs together. Get this wrong, and your schema simply cannot represent the reality of the trading floor. Which brings us to a notorious architecture smell. We've all seen this. Under severe deadline pressure, a developer might try to avoid creating a new table by cramming a many-to-many relationship into a single text column. For example, storing regulatory report IDs as comma-separated text right on the trade row, like RPT1, RPT2. Guys, this is disastrous. It fails first normal form, it completely breaks your SQL joins, and it makes straight-through processing literally impossible, because you have nowhere to store the relationship's own facts, like the submission date or the approval status. You absolutely must model this as a proper associative table.
Furthermore, we have to enforce what we call weak entities. A weak entity is entirely dependent on its parent for its very identity. Think about a cash flow. A cash flow has zero reason to exist without the trade that generated it, right? It cannot outlive its trade. So, from a database mechanics perspective, we model it with a foreign key using an on-delete cascade constraint. That way, if the parent trade is canceled or deleted, the database automatically wipes out the associated cash flows. This guarantees you never end up with orphaned financials artificially bloating your P&L.
Section 6. Masterclass Key Takeaways. We have covered an immense amount of ground here today, tracing the path from the physical shouts on a chaotic trading floor all the way down to strict on-delete cascade database constraints. Let's wrap up with the essential modeling rules you need to take away from this.
Remember these 5 steps, because they are literally the grammar you're going to use to write every schema for the rest of this program. First, separate entities from attributes. If it's a shared concept, it's an entity. Second, use cardinality to define your physical constraints. Third, build associative entities for complex many-to-many links, especially if they carry their own facts. Fourth, relentlessly protect your weak entities to avoid orphaned data. And finally, always view your entity relationship model not as some pretty drawing for a presentation, but as your strict, pre-DDL blueprint.
Now that our entities and relationships are sketched out, we have to ask ourselves a pretty provocative question. If your schema lacks the proper keys to uniquely identify real-world business events, how can you ever truly trust your P&L reporting? Join me in Chapter 3, where we're going to lock these entities down with primary keys, surrogate keys, and normalization to ensure our ETRM data is completely bulletproof. I'll see you in the next explainer.
Welcome back to this explainer on Chapter 3 of our Durga Analytics Premium track. I'm your host and lead trainer, and I've spent decades building, scaling, and, let's be real, occasionally rescuing energy and commodity trading systems. Today, we're tackling what is easily the very first and absolutely the most expensive design choice in any ETRM system: trade identity. Look, when a desk books a 100,000-barrel crude oil trade, losing track of its true identity downstream doesn't just throw a minor database error. No, it causes multi-million-dollar P&L discrepancies. As you know, the program you're in right now, ETRM Data Engineering and Analytics, is literally the only program out there that teaches modern data engineering on a complete, real ETRM platform. We go from the canonical trade model all the way to a signed-off P&L, built entirely end-to-end by you. And right now, we are laying the foundational bedrock for that entire system. All right, let's take a super quick look at our agenda. We're going to start with a little context, define our 3 kinds of keys, and then move from the dangerous illusion of stable business references to the enterprise solution of surrogate keys. We'll touch on the composite key exception and finally wrap up with how identity powers your whole downstream pipeline. Section 1, the context. Let's quickly reorient ourselves and look at where this chapter fits into our overall architecture journey. Our complete program is organized into 12 core modules. We cover a ton of ground, starting with Module 1, Data Modeling for ETRM Systems. Then we move through Reference and Master Data, Trade Lifecycle and Instruments, FPML and Trade Representation, Market Data and Curves, Position and P&L Models, Counterparty and Credit Limits, Data Lake and Warehouse Architectures, Event Sourcing, Streaming and Real-Time Risk, Real-Time Dashboards, and finally, our capstone on straight-through processing.
We are currently right here in Module 1, specifically Chapter 3. We're building the foundation to ensure that every subsequent course, from market data curves all the way to real-time risk, can join trades without an ounce of ambiguity. Make no mistake, if we don't get identity right today, literally none of those downstream systems will work.
Moving on to Section 2. Let's start by defining our vocabulary precisely, because as data engineers, the database constraints we choose do some really heavy lifting. The crucial point here is that identity isn't just some abstract database technicality. It is the absolute bedrock of a trustworthy ETRM platform. If you're a risk analyst or a developer, you have probably spent a late night or several debugging a broken value at risk calculation, or trying to figure out why an endure or right-angle batch process just completely failed. 9 times out of 10, it comes down to a bad join. And a downstream join is only as trustworthy as the key it joins on. Simply put, if your key is unstable, your P&L is unstable. In a trading database, we really rely on 3 distinct kinds of keys. First up, primary keys. This is for row identity, the absolute truth of what makes 2 rows distinctly different things, enforced by a primary key constraint. Second, we have foreign keys, like an instrument ID, which enforce relationships and guarantee referential integrity across the system. And finally, candidate keys, like your external trade reference. These are unique business attributes enforced by a unique constraint. Now, they could technically serve as an identity, but using a candidate key as your primary key is a massively dangerous trap. Let me show you why. Which brings us to Section 3. The natural key disaster, or what I like to call the illusion of stable references. The tempting choice for a lot of junior architects is to use the natural business reference, like a crude oil ticket typed in by a trader, as the primary key. I mean, everyone knows it. It's right there on the screen. Why not use it? Well, let's examine a real-world production incident. Imagine a crude oil trade labeled BLK 88021. When a trader agrees to a deal, the desk needs a human label. They quote it on the phone, email it, drop it in instant messages. It feels permanent, right? Wrong. Human-readable trade references are just mutable sticky notes. They are absolutely not stable identities. Let's actually trace the timeline of this disaster. Imagine the trade is booked on March 2nd. A few days later, someone spots an error, maybe the wrong delivery point, so the booking system cancels that trade. Fast forward a few weeks to March 20th, the upstream system, maybe an exchange or a middle office tool, throws that canceled reference number right back into the pool of available tickets. A trader picks it up and reuses that exact same reference, BLK 88021, for a brand new, completely unrelated trade. If your database treats that human label as the true primary key, boom, you've just caused a massive data collision. And here is the terrifying reality for any data engineer trying to fix this. It is entirely unfixable downstream. Once those 2 distinct trades share the exact same primary key, their cash flows, their amendments, and their P&L merge irrecoverably. You literally cannot write a SQL query to untangle what the identity key itself has conflated, because the database genuinely believes these 2 separate financial events are the exact same object. We are talking about millions of dollars in calculation errors stemming from this one single architectural mistake. Okay, Section 4. To prevent this entire class of failure, we have to implement a firm discipline across our ETRM architecture. If you take absolutely nothing else away from this entire program, please remember this golden rule. Identity must never depend on a value you do not control. Business references drift. People make typos and correct them. Firms merge and suddenly change their naming conventions. A surrogate key assigned by the database once and never, ever reused is the only way to provide a stable spine for your enterprise. When you compare the two, the choice between natural and surrogate keys literally dictates the stability of your platform. Natural keys are mutable. They're prone to human error, and when they inevitably change, they break all your downstream joins. we absolutely must rely on the surrogate discipline. This is a stable, strictly meaningless, system-generated identifier. Think of it as an unalterable genetic fingerprint for your data. In fact, mature enterprise-grade platforms like Ander or RightAngle all key trades internally on a system-generated ID that is completely isolated from the desk's booking reference. Let's actually look at how this is implemented in SQL, because the beauty of the surrogate discipline becomes crystal clear here. We generate a meaningless trade underscore ID as the primary key, but we keep the external ref as a unique candidate attribute. This surrogate key makes two trades mathematically distinct. It allows the external reference to be corrected or even reused upstream without breaking a single foreign key in your cash flows, your position models, or your risk tables. You let the humans use the business reference, but the machine trusts the surrogate. Now for Section 5. We've established surrogates for single entities, but we need to pivot for a second and talk about the composite key exception. So when is a composite key actually the right choice? Use it when identity is genuinely multi-part. Think about bitemporal market data, like natural gas curve marks. The identity of a curve mark isn't just a single opaque thing. It's a genuinely multi-part bitemporal grain. We care equally about two time axes here, the valid time, representing the actual market rate for a specific date, and the recorded time, representing exactly when the system logged it. If you just threw a meaningless surrogate key on a temporal table like this, you'd accidentally allow two rows with identical business axes to coexist. So a composite key is absolutely essential here to honestly enforce the grain and forbid illegal duplicates. All right, our final section. Let's see how this stable spine of identity powers the entire commodity trading business. Zooming out to the broader ETRM pipeline, we can see exactly how this works. We only store one true fact, the trade itself. But every single process after that, enriching reference data, calculating positions, valuation, P&L, right down to audit-ready reporting, is essentially just a database query. And every single one of those queries relies absolutely on that stable surrogate identity to join correctly and avoid silently disagreeing with the rest of the business. Because think about it. If your key breaks at step 1 because someone typed a natural key in twice, that error cascades like wildfire. It corrupts the position net, which distorts the valuation, which throws off the P&L, and completely misshapes the risk exposure. By the time this cascade of errors reaches your settlement team or an external audit, you have lost all lineage and all trust in your data platform. That is why getting identity right is absolutely non-negotiable. To wrap things up, here are your 5 critical takeaways for building a failure-proof data model. Number 1, identity is your first design choice. 2, natural keys drift and get reused, so do not trust them as primary. 3, keep your business references as unique, correctable attributes. 4, point all your downstream foreign keys directly at the meaningless surrogates. And 5, only use composite keys for genuinely multi-part bitemporal grains. I'm going to leave you with this thought as we conclude. We've settled identity, right? Every entity now has a stable key. But how do we ensure the facts hanging off those keys aren't redundant? How do we avoid repeating ourselves? Well, that question perfectly tees up Chapter 4 in our ETRM data engineering track, where we are going to dive deep into the discipline of normalization to the third normal form. Thank you so much for joining me. Keep these principles in mind on the floor, and I will see you in the next explainer.
Welcome back to Durga Analytics' comprehensive ETRM data engineering program. I'm your trainer, and today we're going to master a concept that literally holds the trading floor together. We're talking about how to structure and safely store millions of trading facts without a single contradiction. Just a quick reminder, this is the only program out there that teaches modern data engineering on a complete, real ETRM trading platform. We are going end-to-end from modeling the canonical trade to a signed-off P&L, all built completely by you. So, let's get right into it.
Okay, here's our structural breakdown for today's lesson. We'll cover Section 1, the ETRM data foundation. Section 2, redundancy and trading bugs. Section 3, the 3 data anomalies. Section 4, normalizing to 3NF. Section 5, the architect's dilemma. And finally, Section 6, core truth versus analytical speed.
Starting things off with Section 1, the ETRM data foundation, where we build the core of commodity trading. First off, let's quickly reorient ourselves on where we are in our journey, because honestly, context is absolutely everything when you're designing enterprise systems. Our program is organized into 12 comprehensive modules. We cover the whole shebang, from data modeling and reference data through trade life cycles, market data, position modeling, counterparty credit, all the way to data lakes and real-time risk. Right now, we're wrapping up the foundational groundwork of Module 1 data modeling for ETRM systems, specifically Chapter 4. Normalizing our core to the third normal form is exactly what lets reference data change a fact in one single place while ensuring every trade, position, and end-of-day risk report sees it seamlessly. It's the crucial groundwork we need before we tackle the canonical trade in Chapter 5, because if we don't get this right, everything downstream, settlement, valuation, compliance, will literally fail.
I want you to keep this enterprise principle front and center throughout this explainer. Redundancy is not just some inefficient use of space, it's a ticking time bomb for system integrity. You know, in a standard consumer app, a duplicated fact might just be a tiny glitch on the screen. But in a commodity trading platform handling physical crude oil cargoes or complex power derivatives, a duplicated fact means a wrong number that a trader or risk manager is actively making decisions on. We're talking millions of dollars trading on these numbers every single day. If your risk report says one thing and your finance system says another, you've completely failed the core mandate of an ETRM system.
Moving on to Section 2, redundancy and trading bugs. Let's see what happens when facts disagree.
Let's look at exactly how that bomb goes off by looking at a devastating real-world production incident. We're going to see what happens when a system is built for pure convenience rather than actual truth. Picture a crude oil desk that keeps its trades in a giant, denormalized wide table. Maybe to save report generation time and avoid writing SQL joins, a well-meaning developer decides to just copy the counterparty's credit rating directly onto every single trade row. Sure, it seems super efficient at first. Everything's right there, no lookups needed. But check out the result. We end up with trade A showing Mercuria with an A rating and trade B right next to it showing Mercuria with an A- rating.
Now here is where it gets really interesting and painful. One day, Mercuria gets downgraded by the credit agencies to an A-. Someone runs an update script on that massive wide table, but boom, it hits a timeout or a lock, and only updates a subset of the rows. This partial update leaves conflicting ratings scattered across the entire database. Fast forward to that evening, the risk analyst runs the end-of-day credit report that aggregates exposure by rating band. And guess what? Mercuria is double counted. Their exposure shows up in both the A band and the A- band. Suddenly, limit breaches are firing, alarms are going off, and the desk literally cannot trust its own risk numbers. And the craziest part? Nobody typed a wrong figure. The flawed structure of the data itself invited the disaster.
That brings us to Section 3, the 3 data anomalies which define this structural failure. That Mercuria incident wasn't just bad luck. It's a symptom of deep structural failure. Database architects actually classify these failures into 3 distinct anomalies, and if you're building an ETRM, you absolutely must know these by heart. First up is the update anomaly, which we just saw. If a fact is copied everywhere, updating it means you have to touch every single row. Miss one, and your system disagrees with itself. Second, the insertion anomaly. Imagine you've spent months legally onboarding a massive new LNG counterparty, but your database model forces counterparty details to live directly on the trade row. You literally can't insert this new counterparty into your system until they execute a physical trade. That completely breaks the business workflow since risk and legal need to set limits way before trading starts. Third, we have the deletion anomaly. What if a power desk deletes their final erroneous intraday trade with a specific counterparty? If the counterparty data only lives on that trade row, deleting the trade accidentally wipes the counterparty's entire master record from existence. Yikes.
Let's fix this in Section 4, normalizing to 3NF and curing these anomalies.
So what's the cure? How do we guarantee our ETRM platform represents the absolute truth? We progress through the normal forms until we hit the third normal form, or 3NF. Let's break this down simply for trade data. Step 1. First normal form. No repeating groups. Your trade row shouldn't have a comma-separated list of monthly cash flows stuffed into a single cell. Each cash flow gets its own distinct row. Step 2. Second normal form. No partial dependencies if you're using a composite key. If your key is trade ID plus delivery month, a fact like trade date applies to the whole trade, not just the month, so we move it up. Finally, third normal form, the promised land. This means no transitive dependency via a non-key. In plain English, every non-key attribute, like that problematic credit rating, must depend strictly on its own entity. It depends on the counterparty, not the trade, so it has to be yanked off the trade row entirely.
When we actually write this out in SQL, the business reality perfectly matches the relational model. By creating a dedicated counterparty master table, that credit rating lives in exactly one place. Then our trade table just holds a simple counterparty underscore ID that acts as a pointer back to that single source of truth. We aren't mindlessly copying data anymore, we're just referencing it. Now, if the credit risk team updates a rating from A to A-, they update one row. Instantly, across the entire system, every single trade querying that counterparty pulls the correct updated rating. Those three data anomalies we talked about, they are now structurally impossible.
But this introduces Section 5, the architect's dilemma, knowing exactly when to stop.
Here's the thing. As a data architect or developer building an enterprise ETRM, you're going to hit a wall. Once you learn normalization, the natural instinct is just to keep going, right? So the question is, when is it time to pump the brakes? Should you push past 3NF towards Boyce Codd normal form, or even 5NF for ultimate theoretical purity? Look, you might find a rare edge case where going to 5NF makes academic sense, but in a real-world enterprise environment, it's a massive trap. Going too far creates what we call an architecture smell. You wind up with a hyper-normalized, deeply fragmented schema where just fetching one simple trade requires a 12-table join. Developers will hate working with it, and it brings system performance to an absolute crawl, which is a nightmare when you're trying to read massive option chains or high-frequency forward curves.
So how do we balance this? That's Section 6, core truth versus analytical speed.
This is the fundamental tension in commodity trading platforms. We have to balance the strict, uncompromising truth of the transactional core against the blazing fast demands of analytical dashboards. In database land, it's the classic OLTP versus OLAP divide. So here's the enterprise solution. We rigorously normalize the transactional core, the right model, to 3NF. That guarantees that invalid states are unrepresentable, trade capture is rock solid, and the system simply cannot lie. But a risk analyst does not want to run a complex multi-table join just to see P&L by desk by month. So for the analytical mart, the read model, we deliberately denormalize the data into wide, intuitive star schemas built for rapid querying. Simply put, you normalize for truth and you denormalize for speed.
Let's lock in 5 key takeaways from today. 1. Redundancy is future disagreement, period. 2. Normalize your transactional core to 3NF. 3. Multi-storing facts directly causes update, insertion, and deletion anomalies. 4. Stop at 3NF for the core. Don't over-engineer yourself into a corner. And 5. Our golden rule. Denormalization is only acceptable in a derived analytical layer. That data mart has to be continuously rebuilt from the 3NF core. You never let analysts edit the denormalized mart directly, because if that mart is a strictly derived view, your dashboards can never drift from the absolute truth. The second they do drift, you trigger the classic risk dashboard disagrees with finance disaster, and trust in the ETRM evaporates.
All right, that wraps up Chapter 4. Let's move right into Chapter 5 and see how all this builds. Because now that you know exactly how to safely structure facts, cure anomalies, and balance truth with speed, you are perfectly equipped to model the canonical trade itself. We're going to take everything we just learned and apply it to the single most important entity in your entire platform. But I want to leave you with a thought. If the canonical trade is the beating heart of your ETRM system, what happens to the business if that heart starts pumping corrupted data? We'll tackle that exact scenario in our next lesson. See you there.
Welcome back to The Explainer. I'm your host, and as your resident ETRM trainer here at Durga Analytics, today I'm taking you through a truly critical masterclass. We are going to model the beating heart of your trading architecture. Look, if you're a data engineer, an architect, a business analyst, or a developer working in energy and commodity trading, this right here is where the rubber meets the road. Getting this specific data entity right, designing it for scale, for precision, for rock-solid stability, literally dictates the absolute success or failure of your entire enterprise platform. Real quick reminder on our overall course structure for ETRM data engineering and analytics. This program is the only one out there that teaches modern data engineering by building a complete, real ETRM platform totally from scratch. We're building it end to end. And these first 6 foundational modules, they lay down exactly how we capture, model, and value our commodity trades. Why do these first 6 matter so much? Well, because they are about establishing absolute structural integrity before a single drop of data is ever allowed to hit your valuation engines. And once we get that foundation rock solid, we're going to scale all the way up through modules 7 to 12. This is where we take all that incredibly clean data, push it into the data lakehouse, apply event sourcing, and build out our streaming real-time risk. Ultimately, this exact path shows how we get from a raw captured deal on the trading floor all the way to a signed-off P&L at the end of the day. But right now, we are squarely in Module 1, Chapter 5, the canonical trade entity. We are defining the single canonical trade record that every subsequent course, every downstream system, and every risk analyst is going to attach to. If you get the trade entity right, 11 subsequent courses compose on it seamlessly. But if you get it wrong, every downstream system inherits that flaw. So here's our agenda for this chapter. We'll start with the ETRM data foundation, move into the economic ground truth, talk about keeping the entity clean, using data types as controls, building the enterprise integration hub, and finally wrap up with our key takeaways. Let's dive in. Section 1, the ETRM data foundation. Let's start by looking at what a trade actually is from a first principles business perspective. Before we even think about writing a line of SQL or designing a database schema, we really have to understand the business we're modeling. In commodities, whether you're moving physical crude oil, natural gas, massive LNG cargoes, or trading financial power, a trade is a very specific, highly structured type of contract that binds 2 parties together. Which brings us to Section 2, the economic ground truth. Because before we start spinning up tables, we need to understand this truth exactly as a trader sees it on the floor when they execute a deal. If we don't capture the raw economics perfectly at the point of origin, I guarantee you, every risk aggregation and P&L calculation we build on top of it will be fundamentally broken. Take a look at this trade capture screen. Notice how it takes a really complex financial agreement and boils it down into very simple, distinct fields. Whether you're trading 10,000 barrels of WTI crude, injecting natural gas into storage, or structuring a 5-year baseload power contract, the database only cares about the absolute core agreement happening right here in these specific fields. All that visual noise, the flashy dashboards, the validation pop-ups, that's just UI. The data architecture focuses strictly on the irreducible facts. So, stripping away all the industry jargon, what is a trade? It's simply the frozen economic agreement between 2 parties. That is it. It's exactly what was agreed upon at the exact moment the deal was struck, stripped of all subsequent life cycle events. Think of it kind of like a receipt at a cash register. The core facts of that purchase are completely frozen in time, even if you decide to return or exchange the item a week later. It's an unchangeable snapshot of a commitment.
The crucial point here is this. If we buy 10,000 barrels of WTIK6 from Mercuria at $72.40, those exact details form the absolute economic core of our database record. You've got direction, quantity, instrument, price, counterparty, date, and your internal book. If you have those 5 to 7 facts, you have the entirety of the trade. And for the data architects listening right now, these irreducible facts absolutely must be tied to strictly enforced foreign keys in your schema. That's how you guarantee referential integrity across the whole system.
Okay, section 3, keeping the entity clean. Now that we actually know what a trade is, we have to enforce probably the hardest architectural discipline for any data engineer, which is knowing what does not belong on the trade table. I know, it is incredibly tempting during a dev rush to just throw every piece of related data into this one central table. But doing that invariably creates a massive, unmaintainable mess that will totally cripple your system's performance. You have to be absolutely ruthless here. Exclude stateful data like confirmations and derived data like mark-to-market. Why? Because they happen around the trade, not inside it. Think about it for a second. A confirmation status might change 3 times over a couple of days. Mark-to-market? That changes every single time the market curve moves. If you store these on the trade table, you're constantly overriding your core economic record just to update a temporary status. In a database, that constant updating causes row locks and massive performance bottlenecks, especially if you're in a high-frequency or high-volume trading shop. To really drive home why this matters, let's look at a real-world production incident that has burned so many ETRM developers. Imagine this. You get a frantic call from the risk desk. 2 different trading screens are showing 2 completely different mark-to-market values for the exact same crude oil trade. The pricing engine didn't miscalculate anything, so what went wrong? Well, here is the autopsy of that failure. A well-meaning developer tried to optimize screen B by caching the MTM directly on the trade table as a new column called current_MTM. But overnight, the batch valuation engine recomputed all the marks from the new market curves. Screen A read directly from the new valuation table. Screen B? It read the stale cache sitting on the trade table. The result was a massive enterprise reconciliation failure right at the high-stakes end-of-day cutoff and sheer panic on the trading floor. This is exactly why derived values absolutely never belong on the canonical trade entity. Moving on to Section 4, Data Types as Controls. To prevent nightmares like that, and to build a truly robust ETRM, we have to treat our database columns not just as storage containers, but as strict financial controls. This isn't just about saving bytes on a hard drive, folks. It is about protecting the firm's balance sheet at a structural level. Listen, you must never, ever use floating point data types for money or quantity. A tiny floating point rounding error on a multi-million-dollar LNG cargo or a massive 5-year power contract, that translates into real unrecoverable lost dollars for the firm. Instead, you use explicit numeric types with fixed, exact precision. You use a single constrained character for direction, like a B for buy and an S for sell. You enforce proper time zone-aware date types. Your database schema itself needs to be your very first line of defense against bad data. Section 5. The Enterprise Integration Hub. When you combine those strict economic facts with precise data types and really tight constraints, something amazing happens. The canonical trade entity totally transforms. It actually becomes the Rosetta Stone of your enterprise integration hub. Just look at how the data flows here. The canonical trade is captured exactly once, and it acts as this singular central hub that every downstream system relentlessly relies on. Trade capture sends the deal in, it hits this core canonical hub, and from there, it perfectly and dependably feeds the position calculations, the valuation engines, and the settlement workflows, all without a single drop of duplication. And this brilliantly illustrates the ultimate ETRM design pattern. We store exactly one frozen fact, the trade, and we let all 8 downstream views query it. Reference data enriches it, market data prices it, position nets it, valuation multiplies it, all the way down to risk and reporting. Because everything is querying that one single clean, canonical record, nothing can ever silently disagree. This is exactly how you eliminate that dreaded silo problem, where risk and finance show up to a meeting with 2 totally different numbers for the exact same portfolio. Finally, Section 6, Key Takeaways and Next Steps. Let's wrap up this lesson by really solidifying the data contract you are creating for your business analysts, your developers, and your risk teams. Because when you design this table, you are establishing a foundational contract that the entire enterprise will rely on. So if you remember only 5 things from this masterclass, please make it these. Keep the economic agreement frozen. Push derived values like MTM out of the table. Never overwrite original records for amendments. Use lifecycle events instead. Enforce strict numeric precision. And finally, treat this canonical trade table as a stable enterprise contract. Change it deliberately and change it rarely because you've got 11 other modules built directly on top of it. All right, so we've established that a trade simply points to a specific instrument, a counterparty, and a book. Let's move to our next steps and see how this builds into Chapter 6 on instruments. But before we get there, I want to leave you with a bit of a provocative thought. If our perfectly clean canonical trade is really just a frozen pointer referencing an instrument, what happens to your entire platform's historical risk and P&L if someone accidentally alters that shared instrument definition? Think about that for a minute, and I'll see you in the next chapter. Welcome back to The Explainer. I'm your expert trainer from Durga Analytics, and today we're diving straight back into the canonical trade model. If you're a data engineer, an architect, a business analyst, or a developer in this space, you already know that the data model is the absolute bedrock of any energy trading and risk management system. Today we're tackling a massive piece of reference data: instruments, products, and contract templates. We're going to look at exactly how to represent these reusable structures cleanly so your trading platform can actually scale up without falling apart under its own weight. Just to give you a quick "you are here" moment, this training is part of our comprehensive ETRM data engineering and analytics program. This is the only program out there that teaches modern data engineering on a complete, real-world ETRM platform, taking you all the way from the canonical trade model right through to a signed-off P&L. We've got 12 modules in total, and right now we are deep into Course 1, specifically Chapter 6. In our last chapter, we finalized the trade entity, but we left one huge, incredibly important piece of reference data hanging: the instrument. I really want you to let this quote sink in for a second. Model the instrument once, and 1,000 trades share it. Model it wrong, and everyone inherits the flaw. Listen, in enterprise data architecture, the stakes are incredibly high. The instruments we're modeling today, they're the reference data that your governance teams manage, that your market data curves attach to, and that your valuation engines actually price. If you get this wrong at the root level, your P&L and your risk reporting will be structurally compromised. No pressure, right? Okay, here's our roadmap for today. First, we'll cover the trade versus instrument split. Second, the product, template, and instrument structural hierarchy. Third, we'll talk about diagnosing and fixing ETRM architecture smells. And fourth, we'll wrap up with the essential key takeaways. All right, let's dive straight into Section 1, the trade versus instrument split. Okay, so mastering exactly what belongs on a trade versus what belongs on an instrument is a classic interview check for any senior ETRM role. Honestly, getting this right is the secret to a perfectly clean canonical trade model. The big aha moment here is that hundreds of different trades can all point to the exact same instrument. Think about it. Your crude desk might buy a WTI K6 futures contract on Monday and then sell that very same WTI K6 contract on Tuesday. Both of those trades are referencing one single instrument. The instrument itself is where what was traded is fully defined. We're talking the commodity, the grade, the delivery month, the contract size, the unit of measure. None of that, literally none of it, belongs on the trade itself. If you stick the unit of measure on the trade entity, you're forcing your users to re-enter it thousands of times, which is a guaranteed recipe for data drift. The instrument has to be a strong, independent entity. It exists completely independent of whether any specific trade references it or not. So you model it once, you key it with an instrument ID, and you just have your trades point to it. Simple as that. Moving right along to Section 2, Product, Template, and Instrument.
Now, what's really interesting about this structural hierarchy is how perfectly it solves the data redundancy problem. Because in a real system, we don't just have a flat list of instruments. We use a 3-tier hierarchy. Right at the top, we have the product, for instance, WTI futures. This level holds all the shared terms: the commodity, the unit of measure, the contract size, the exchange. Then, moving down one level, we have the contract template. Think of this as the reusable pattern. It basically says, hey, given a delivery month, I'll stamp out a fully specified instrument for you. And finally, down at the leaf level, we have the actual tradable instrument itself, like WTIK6 or WTIM6. The key here is that the instrument only carries information that is uniquely its own. So the specific month, the symbol, and the expiry date. Everything else? It just inherits it from the top.
So let me throw a real-world architect's dilemma your way. This is exactly the kind of decision you'll face when designing trading marts or data lakes. You have a contract size. Let's say it's 1,000 barrels for standard WTI contract. Where exactly does that specific data point live in your physical schema? You basically have two choices. Option A is putting it on each individual instrument, so it's super easy to query. Option B is putting it all the way up at the product level, where it's referenced by every instrument in that family. Now, option A is incredibly tempting for beginners, but option B is what actually survives in production. Why? Because the contract size is a property of the entire WTI futures family, not just the May contract or the June contract. Storing it on the product means you're storing it exactly once, which keeps you nicely in third normal form. Every single instrument just inherits that size by reference. If you decide to go with option A, you are practically begging for a massive production incident. Let me share a quick horror story with you. Imagine an exchange suddenly decides to change a contract size. It happens. If you stored that size on every single monthly instrument, your operations team now has to go in and manually update dozens, maybe even hundreds of individual instrument records. It is virtually guaranteed they're going to miss one. And suddenly, your risk system is calculating exposure based on 1,000 barrels for May, but 500 barrels for June, all because of a tiny data update anomaly. It's a mess. But if you used option B, an exchange changing the size is just a single one-row update on the product table, and boom, every single instrument in that family inherits the fix instantly. Which brings us nicely to Section 3, Fixing ETRM Architecture Smells. You see this all the time. Under pressure to deliver, development teams will often build completely separate, disconnected tables for every single instrument type. They'll spin up one table for futures, a totally different table for physical gas, and yet another one for OTC swaps. So why does this rot your architecture? Well, because suddenly a trade can't just uniformly reference an instrument. Every single query or report you write that joins trades to instruments now has to know the specific commodity type before it can even run. You end up having to write these massive, incredibly brittle union statements all across your data warehouse. And the kicker? Whenever a new commodity type gets introduced next quarter, you have to go back and touch every single join in your entire system. It's an absolute nightmare. And this setup right here brilliantly illustrates the correct enterprise approach. You maintain one single instrument entity with a shared core, so product, symbol, and month. Every single trade in your entire system, whether it's power, gas, agriculture, whatever, references that exact same instrument ID uniformly. Then, what you do is hang the type-specific details off that core as extensions. So physical gas extends the core with delivery points and nomination terms. Options extend it with strike prices and call/put flags. You resolve everything down to one instrument entity, which allows one single trade table to serve every commodity in the business seamlessly. And just to ground all this theory in physical reality, let's look at how the heavyweight commercial platforms handle this. Endure models this precisely using its instrument and toolset layers. Allegro and Right Angle, they use product and instrument masters with the exact same product then instrument layering that we just walked through. The naming conventions might tweak slightly depending on the vendor, but absolutely all of them fundamentally separate the reusable family definition from the actual tradable dated instrument. By mastering this, you aren't just learning some abstract data model, you're literally learning the underlying mechanics of the most robust trading platforms in the world.
All right, let's wrap this up with Section 4, Essential Key Takeaways. So the crucial point is this. If you remember absolutely nothing else from this explainer, please lock in these 4 unbreakable rules. Number 1, an instrument is the tradable thing and it is defined exactly once. Number 2, always lift shared terms up to the product family to kill data redundancy. Number 3, only genuinely per instrument facts like expiry dates should live down at the leaf level. And number 4, the unit of measure and the contract size must always be resolved through the instrument. Never store them directly on the trade. By rigorously applying these rules, your trade model is now clean, it's highly scalable, and it's totally insulated from reference data anomalies. But a trade doesn't happen in a vacuum, right? We've perfectly modeled the instrument that we're trading, but what happens when the entity on the other side of this transaction defaults on their obligation? How do we actually map out the incredibly complex web of legal entities and parent companies to calculate our true exposure? Well, that provocative challenge is exactly what we're going to tackle next as we transition into Chapter 7, Counterparty, Credit, and Limit Modeling. Thanks for tuning in to this Durga Analytics training, and I can't wait to explore the next layer of the ETRM ecosystem with you. See you there. Welcome back to The Explainer. I'm your host, and today we are jumping right into a Durga Analytics masterclass. We're rolling up our sleeves as expert practitioners to really dig into the architecture of modern energy and commodity trading systems. Look, if you're a data engineer, an architect, a business analyst, or a risk manager, this is exactly where the rubber meets the road. We're going to unpack the data models that literally protect a trading firm from complete financial disaster. So, let's get into it. Real quick, before we get too deep in the weeds, let's just map out where we are in the overarching ETRM Data Engineering and Analytics program. This is the 12-module roadmap that takes you all the way from the canonical trade model to a fully signed-off P&L. We are currently right in the thick of Module 1, which is all about data modeling. And specifically, we're tackling Chapter 7 today, Counterparties, Legal Entities, and Hierarchies. All right, let's kick this off with a quote that honestly should be framed and pinned to the wall of every single trading floor and IT department on the planet. You do not trade with a name. You trade with a legal entity that can default. Model that, or your credit risk is fiction. Really think about that for a second. In the incredibly high-stakes world of crude oil, LNG, or power trading, a vague corporate label doesn't owe you millions of dollars. An actual, specific, incorporated company does. And that brings us to a trap that I like to call the counterparty illusion. Imagine you're processing a trade ticket, let's say TRD 1001, and you just see a field that says Mercuria or Glencore. It's such a common beginner's mistake, usually carried over from legacy spreadsheets and old data entry habits, to just model that as a single flat text field in your database. But treating it as a flat name, that is a fundamental modeling failure. That one simple label is actually hiding 3 totally distinct concepts. And if you blur them together, you are absolutely going to break your settlement and risk systems down the line. So what happens when we actually break down a single name? Well, we find out exactly what we're dealing with. We essentially have 3 distinct concepts: the counterparty, the legal entity, and the group.
First up, the counterparty. This is simply the role. Who is on the other side of this specific transaction. Second, we have the legal entity. This is the highly specific incorporated company that is legally obligated to pay you, like Mercuria Energy Trading SA. If a natural gas cargo isn't delivered, you need to know exactly which entity you're actually taking to court. And finally, the group. This is the broader corporate family, which tells us who we are exposed to in total. You literally have to model all three because they answer three very different business questions. Who's on the trade, who owes the money, and who are we exposed to overall? Which leads us to a really crucial point, the enterprise principle for counterparties. The core rule here is that a trade must always reference a specific legal entity, never just a loose generic name. Things like identity, obligation, and default, those are all strictly entity-level facts. This means your trade capture systems have to be locked down to only allow leaf entity selection, period. If you need to know the group or calculate the total aggregate risk, you don't store that flatly on the trade ticket. Instead, you derive it by walking up the corporate hierarchy. This exact principle is what separates your amateur, cobbled-together spreadsheets from a truly governed enterprise-grade ETRM system. To visualize how this actually maps out, think of it like a massive tree. Your shared terms and your global master agreements, those live right at the top root, the ultimate parent group. But the actual physical natural gas or metals trades you're executing, those hit the specific leaf branches way down at the bottom, like SA Geneva, US Inc., or Asia PT. The golden rule is that only what is genuinely per leaf lives at the bottom, and then the financial exposure is systematically rolled all the way back up to the root.
Now let's pivot over to the engineering side and talk about how we actually build this out in practice. For the data architects and ETRM developers listening, think about how you structure your SQL DDL script. The magic bullet here is the parent ID column. It's designed to point right back to the legal entity table itself. This self-referencing foreign key is incredibly elegant because it captures arbitrary hierarchy depth. You don't need to run complex, risky database migrations every single time a counterparty reorganizes its corporate structure. Whether you're tracking a tiny trading subsidiary rolling up to a regional holding company or traversing all the way to the ultimate parent, this one single column handles the whole shebang. It's a highly reusable pattern you are going to rely on constantly.
But to make this self-referencing tree actually work on a global scale, we have to rely on the LEI, or Legal Entity Identifier. This is another attribute you'd build right into that schema. And look, this isn't just a nice-to-have feature. It is a strict regulatory reality. Credit teams are required to report group exposure accurately, and the whole LEI system exists across the industry, precisely so entities can be tied to their ultimate parents without any ambiguity across the market. It basically guarantees that everyone, from your internal risk analysts all the way up to global regulators, is talking about the exact same corporate entity.
So how does an ETRM system actually process all this under the hood? It boils down to a 4-step recursive aggregation process. Think of it kind of like water flowing up through a plumbing system. Step 1. The new trade enters at the specific leaf entity. Step 2. The system uses that parent ID we just talked about to mathematically pump that exposure up the pipes. Step 3. The exposure aggregates into the main regional holding tank. And finally, Step 4. The total risk is checked right at the ultimate parent level. This exact kind of recursive math is the heavy lifting happening under the hood in the credit modules of massive commercial platforms like Intura, Allegro, and Right Angle.
And out on the actual trading floor, this recursive aggregation is what stops a disaster right in its tracks before execution. Because your system is actively, recursively aggregating exposure up that tree, it catches a credit breach before the deal is even signed. Imagine a trader tries to execute a new deal with a company called Smallco. The system will instantly block it because it calculates that this new trade pushes their aggregate group exposure over their $25 million limit, even if it's just by a fraction of a million. This architecture gives your business the ultimate power to stop toxic, out-of-policy exposure in real time. So, what are the massive financial stakes of getting this right versus getting it wrong? Well, if you rely on a flat name database, your exposure is scattered everywhere. It's hopelessly understated because trades are dispersed across a bunch of different text names that don't mathematically talk to each other. The result? You silently blow right through your group credit limits and expose your firm to massive unseen defaults. Conversely, a governed hierarchy tracks every single dollar of risk accurately back to the parent. It's all about accurate, recursive aggregation, which keeps the firm completely safe and regulatory compliant. To wrap all of this up, whether you are a business analyst writing up specs or a data engineer physically building the pipeline, you need a structural checklist for moving from a loose name to a governed legal entity. Rule 1. Completely separate the counterparty role, the legal entity, and the group. Rule 2. Model your legal entities as a self-referencing tree using a parent_ID column. And Rule 3. Always carry the LEI as a unique attribute to map everything back to global standards. If you follow these rules, your credit foundation is going to be absolutely rock solid. All right, so we've successfully modeled exactly who we trade with on the outside, but I want to leave you with a provocative thought here. How do we model internal ownership? When a trader actually executes a deal, where do our internal books, portfolios, and trading desks fit into this data model? Well, that is exactly what we're going to unpack in Chapter 8. Thanks so much for joining me on this explainer. Keep modeling smart, and I'll catch you in the next one. Welcome back to this expert masterclass explainer from Durga Analytics. I'm so glad you're here today because we're diving into exactly how modern data engineering powers enterprise ETRM trading platforms. Listen, whether you're a data engineer, a data architect, a business analyst, or even a trader right there on the floor, understanding how a trade is structurally organized inside your firm is absolutely critical. We're going to break down the exact data architecture that takes a raw trade and attributes it securely, ensuring your risk and P&L reporting is always perfectly accurate. Okay, let's just jump right in. Just as a quick reminder of our overall program structure, this lesson is part of our comprehensive ETRM data engineering and analytics curriculum. We're proud to say it's really the only program out there that teaches modern data engineering on a complete, real ETRM trading platform. We're currently in Module 1, which is data modeling for ETRM systems, literally the foundational bedrock for everything else we'll do. Specifically, we're tackling Chapter 8 on internal trade organization, books, portfolios, strategies, and desks. We've already covered how to model what we're trading and who we're trading with. Today we figure out exactly where that trade lives inside your firm. Here's our roadmap for today. First, the business ground truth. Second, the architectural solution. Third, implementation challenges. And finally, the enterprise data flow and key takeaways. Part 1, the business ground truth. Let's look at how trading activity is actually organized. You see, a trading firm doesn't just throw all of its trades into one giant, undifferentiated pile. The philosophical foundation of everything we're building today is summarized perfectly by this one idea. A position means nothing until you say whose. Seriously, if you can't attribute a position, you absolutely cannot answer a fundamental question from your management team like, hey, how much did the crew desk make today? Every single P&L number, every risk metric, every settlement, it's all sliced by these organizational containers. So the most granular level of this organization is the book. Think of a book as the fundamental container that a trade is filed into. It serves as that trade's single permanent home. For example, when a trader executes a deal, let's call it TRD-1001, that trade gets immediately filed into a specific book, like, say, OIL1. A trade has one and only one book. Moving one level up the chain, we have the desk. A desk is basically a team of traders with a specific commercial mandate. Let's take the crude desk, for example. The crude desk owns that OIL1 book we just talked about, and they probably own several other related books as well. That book is owned by exactly one owning desk which in turn rolls up to a larger business unit in the organization, perhaps the overarching global oil division. This creates a very strict, undeniable hierarchy of ownership. Now, here's where it gets kind of interesting. We have a completely different concept called a strategy. Unlike a book, which is a physical home, a strategy is a cross-cutting label. It represents trades expressing one specific market idea. Think of something like a European LNG arbitrage or a WTI/Brent spread. This strategy is simply an idea, and it can include trades for many different books executed by many different traders across the floor. Looking at a mock trader dashboard for book Oil 1, you really have to realize that every P&L and risk tile you see isn't just magically generated, and it certainly isn't typed by hand. The net mark to market, the day P&L, the value at risk, all of it is dynamically queried and derived directly from the underlying organizational model we're building right now. Simply put, if our data model for books and strategies is broken, the dashboard is broken. Section 2, the architectural solution. How do we actually build this in the database? For the data architects and engineers listening, the secret sauce here is understanding that we have two fundamentally different relationship shapes to model. On one side, we have a strict ownership hierarchy for books and desks. Every book has one desk. Every desk has one business unit. That's a classic one-to-many relationship. But on the other side, we have strategies. These require a flexible, cross-cutting tag. A single strategy can span many books, and a single trade can belong to many strategies. So that's a many-to-many relationship. To model the ownership hierarchy for books and desks, we're actually going to reuse the exact same self-referencing tree pattern you previously learned in Chapter 7 for modeling counterparties and legal entities. In your database table, an organizational unit simply has a parent ID that references another organizational unit. You learn this pattern once, and you literally apply it everywhere. The trade references its book, and if you need to know the desk or the business unit, you just walk up the branches of that tree. Okay, so the absolute crucial point is this architectural rule. Store only the book on the trade itself. Derive the desk and the business unit by walking the tree. Why? Because if you denormalize the data and directly copy the desk and business unit onto the trade record, you are setting yourself up for a massive maintenance headache. Let's say a book changes hands later. Maybe it moves from the London crude desk to the Geneva crude desk. If you hard-coded the desk, your historical trades will suffer from nasty data drift. So store the book, derive the rest. If you need reporting speed, materialize a derived view, but never, ever hand copy the desk path onto the trade. Conversely, how do we handle strategies? Well, to avoid the architecture smell of forcing a cross-cutting idea into a rigid organizational tree, we model strategies using an associative table, a classic many-to-many mapping table. This simple table links a trade ID directly to a strategy ID. This brilliant little setup allows a trade to keep its single home in its book while simultaneously being tagged to any number of strategies without distorting your fundamental ownership hierarchy. Section 3. Implementation challenges. Let's talk about the real-world stakes when things go wrong. Picture this. It's a weekend system migration. Millions of trades are moving across your systems. A trade gets booked, but due to some weird mapping error, it's saved without a book assignment. It just has a null value for its book. Monday morning arrives. Suddenly, finance raises a massive red flag. The CFO looks at the desk totals, and they sum to less than the firm-wide total. We have a massive reconciliation break, and the CFO is understandably panicking. The question echoing across the trading floor is, where did the P&L go? Let's diagnose this bug together. Because the position by desk reports rely on an inner join to walk up that organizational hierarchy we just built, that specific trade with the null book assignment silently drops out of the desk totals entirely. The join just fails. However, the overarching firm total, which just looks at the raw trades without grouping them by desk, still includes it, so the parts no longer sum to the whole. The enterprise fix for this is incredibly simple, but I promise you it is absolutely vital. You must implement a strict, not null constraint on the book reference right there at the database level. You literally force the system to reject any trade that doesn't have a home. By ensuring every single trade attributes to exactly one book and therefore exactly one desk, you guarantee that your desk totals will always flawlessly reconcile with your firm-wide totals. Section 4. Enterprise Data Flow and Key Takeaways. Let's zoom out and look at the big picture. Take a look at this enterprise data flow. Our securely attributed trade acts as a single, centralized, stored fact. It flows systematically through reference data enrichment, market data curves, valuation, risk exposure, and all the way down to settlement and audit-ready reporting. Because we enforce that single book home and derived our hierarchy, every single box downstream is simply a query over the same canonical data. Nothing can silently disagree. It's beautiful, really. One fact stored, 8 views derived. To summarize everything we've covered in this masterclass, here are your 5 non-negotiable key takeaways. Number 1, trades have exactly one book. It is their home. Number 2, derive desks and business units dynamically by walking the tree, never copy them onto the trade. Number 3, use associative mapping tables for strategies because they are a many-to-many cross-cutting tag. Number 4, enforce not null constraints on your book reference to protect your reconciliation. And number 5, always reuse your self-referencing tree patterns. Learn it once, apply it everywhere. Now that your trade securely knows what it is, who it is with, and exactly where it lives internally within your organization's books and desks, we have to look outside again. Think about it. If a financial trade lives safely in a database book, where exactly does a 2 million barrel physical cargo of crude oil live when it's floating somewhere in the middle of the ocean? How do we architect that? Join me in Chapter 9, where we will model physical locations, delivery points, and complex geography. I'll see you there. Welcome back to Durga Analytics. I'm absolutely thrilled to have you here for this explainer. You're watching a core module from ETRM Data Engineering and Analytics. And if you're new here, this is the only program out there that teaches modern data engineering on a complete, real ETRM trading platform. We literally take you from the canonical trade model all the way to a signed-off P&L built end-to-end by you. Today, we are tackling the exact data architecture needed to govern physical commodity locations. Look, whether you're a data engineer, an architect, a business analyst, a developer, or a risk manager, getting your geography right, it is totally non-negotiable. I want you to let this quote sink in for a second. Cushing typed 3 ways is 3 hubs and a third of your real exposure. Geography must be governed, not typed. Seriously, bad location data doesn't just create messy, annoying reconciliation headaches for the back office. It completely masks massive market risks from your traders and risk analysts. It literally leaves the entire enterprise flying blind. So, here's our game plan for today. We'll start with a quick course overview, dissect a catastrophic fragmented hub failure, look at geography as a governed entity, model out the location hierarchy, and finish up with truthful concentration and risk. Part 1, the ETRM course overview. Let's quickly get our bearings on where we are in your journey. As a reminder, this complete program is organized into 12 core modules. We cover the whole shebang: data modeling, reference and master data, the trade lifecycle, FPML, market data, position and P&L, counterparty credit, the data lakehouse, event sourcing, streaming risk, real-time dashboards, and we cap it all off with straight-through processing. Right now, we are deep into the foundational bedrock of it all, Module 1, data modeling. Specifically, we're in Chapter 9, Locations, Delivery Points, and Geography. The geographic model we're building today is going to act as the ultimate master data, feeding physical operations across this entire program. This is the absolute foundation of your physical forward trades, whether you're moving crude oil, natural gas, LNG, power, metals, or ags. Okay, Part 2, the fragmented hub failure. Let's talk about what happens when things go terribly wrong in production. Remember the missing barrels detective story from back in Chapter 2? We had this crazy situation where a desk dangerously overconcentrated their physical crude trades at the Cushing hub, yet the risk limit system stayed completely silent. Not a single alarm went off. Why did it fail so badly?
Well, the cause was a fundamental data modeling anti-pattern. Because the delivery point was designed as a simple free text field on the trade capture screen, one massive risk was fragmented into 3 supposedly safe chunks. We had trades booked at Cushing with a capital C, Cushing OK, and lowercase Cushing. To the computer system, these looked like 3 distinct, moderate exposures. But in reality, it was one giant limit-breaching position sitting at a single physical hub.
Which brings us to Part 3, Geography as a Governed Entity. Time to fix this systemically. The crucial architectural rule here is this. Delivery location is a governed entity. Every physical trade must reference it via a foreign key. It is never, ever free text. Whether you're trading crude at Cushing, gas at a specific pipeline meter, or power at a grid zone, that shared place has to be a strict entity in your database, just exactly like a counterparty. Think about how tightly counterparty ratings for massive entities like Mercuria or Glencore are governed. You wouldn't let a trader just type in whatever they want for a legal entity, right? Your location master must be just as strictly resolved. A trade names a location by its ID. That way, if you change an attribute on that location master, every single downstream transport or risk calculation automatically inherits the correct effective dated value. Moving right along to Part 4, Modeling the Location Hierarchy. Let's peek under the hood at the actual data architecture required to pull this off inside your ETRM database. Locations naturally nest inside one another, kind of like Russian nesting dolls. A specific delivery point sits within a hub, hubs sit within regions, and regions sit within countries. To avoid a messy, rigid, wide schema, we model this as a self-referencing hierarchy using a parent ID column or a surrogate key. It's a highly reusable pattern that handles infinite geographic depth without needing a separate column for every single level. So, put your data architect hat on for a second. If a trade physically delivers at a very specific pipeline meter within the Cushing hub, which level of this hierarchy should the trade actually point to in your database? You link to the hub because that's the level traders generally talk about, or do you link to the specific point? You absolutely must reference the exact delivery point, the leaf node. If you reference the broader hub, you are literally throwing away the point-level detail that dictates your physical transportation logistics, your tariff costs, and exactly which pricing curves apply. You reference the granular point, and the hub, region, and country are easily derived by just walking up the hierarchy tree when you need them. Part 5. Truthful concentration and risk. When you model the data correctly like this, the business payoff for the enterprise is immediate. To get clean aggregated numbers, we utilize a recursive SQL query, often a common cable expression, or CTE. This allows us to seamlessly roll every specific delivery point up to its parent hub. It's like a giant puzzle coming together perfectly. We aggregate the physical exposure across all trades with 100% accuracy, regardless of which specific subpoint the trader originally booked. Cushing rolls up as one hub, Henry Hub rolls up as one hub. And boom, this brilliantly solves our Chapter 2 detective story. Honest concentration reporting means your chief risk officer can actually sleep at night. A risk manager can trust that a hub showing a huge concentration really is huge, and one showing small really is small. Your limits will actually trigger when they're breached, keeping the entire firm protected. All right, let's review how this translates into your upcoming lab checklist. Remember these 4 vital steps. First, banish free text and model locations strictly as governed entities. Second,
Build your self-referencing geographic tree. Third, ensure your physical trade capture references that specific leaf node. And fourth, use recursive queries to aggregate exposure upward. Get ready to build this all out in the lab. But before you hit the lab today, I want you to think about the practical workflow of a real trading floor. In a strictly governed system, data entry is rigid, but as we know, markets move incredibly fast. You always have to balance strict master data with the speed of front office execution.
Now that your trade knows exactly where it delivers, we're going to tackle quantities and pricing in Chapter 10 by mastering currencies and units of measure. But I want to leave you with one final provocative thought. How exactly will you handle a fast-moving trader who needs to book a massive deal at a brand new location that doesn't exist in your master data yet? Do you halt the trade and lose the market opportunity, or do you risk fragmenting your hub with a temporary override? Think hard about your data governance workflows, and I'll see you in the next chapter.
Welcome back, everyone, to our ETRM Data Engineering and Analytics Masterclass. I'm your expert trainer from Durga Analytics, and if you're ready to stop hard coding and really start engineering, well, you are in the exact right place. Today, we're diving into Chapter 10. Remember, this is the only program out there that teaches modern data engineering on a complete, real-world ETRM trading platform, taking you all the way from a canonical trade model to a fully signed-off P&L. So let's jump straight into today's topic: currencies, units of measure, and conversions. Just as a quick reminder of where we are in the curriculum, you're building a complete enterprise trading platform from scratch with us. Right now, we're deep into Module 1, which is data modeling for ETRM systems, and specifically Chapter 10. The foundational work we're doing right here, it literally underpins every single valuation, position, and settlement amount we're going to build later on. Whether you're a data architect, a developer, or a risk analyst, you have to understand this. If we get the data model wrong today, the entire platform's math is going to fail tomorrow. Okay, here's our quick roadmap for today's masterclass. We'll start by looking at why units give numbers meaning, move into governing units and currencies, and then tackle safe conversions and FX. After that, we'll look at a real-world disaster, the notorious ton-barrel mix-up, before wrapping up with your core takeaways.
Section 1. Welcome to Chapter 10, Grounding the Business Truth. Let's start by establishing a foundational reality of trading data that absolutely every data engineer and architect needs to internalize.
I really want you to burn this concept into your brain. 10,000 of what? Priced in which currency? You see, a raw number on a trade is completely 100% meaningless without its unit and currency context. I mean, 10,000 of what? If it's barrels of crude oil, great, you've got a deal. But if it's paper clips, yeah, you're probably fired. Every quantity on a trade is a number in some specific unit. Maybe it's 10,000 barrels of crude, 50,000 MMBTU of natural gas, or 100 megawatt hours of power. And every price is in some currency per unit, like US dollars per barrel. The number alone tells you absolutely nothing.
Moving to Section 2, units give numbers meaning. Let's see how this foundational truth actually plays out in a real, day-to-day commodity trade.
Take a really close look at a standard trade entry interface. Notice the quantity field showing 10,000? Also notice how there is no unit drop-down next to it for a trader to just, manually select gallons or liters. That is incredibly intentional. The unit of barrels is inherited directly from the WTIK6 instrument itself. It's a fundamental property of the instrument, which, if you recall, we modeled back in Chapter 6. Doing it this way guarantees a single source of truth across your enterprise platform and prevents any contradictions. We are ensuring that a quantity is inextricably tied to what the instrument actually represents in the physical world.
Which brings us to Section 3. Governing units and currencies, and the architectural decisions behind them. If the unit comes from the instrument, how on earth do we architect the conversions when these commodities are traded all over the globe?
Well, in enterprise ETRM systems, you're constantly needing to convert units. Think about converting barrels to metric tons for an imported cargo across various reports. If you take the easy route and just hard code those conversion factors into the SQL or Python scripts of separate reports, they are inevitably going to drift. It happens all the time. Someone updates one report but completely forgets another, and suddenly, boom, you have two correct reports producing massive valuation mismatches. Instead, and this is an absolute best practice, you must store these factors once in a governed, dated reference table that every single report looks up. Conversion factors are reference data, folks, and reference data lives in databases, not in your code.
From a pure data engineering perspective, you always want to use high-precision data types for your conversion factors. We're talking something like numeric 20,10. Why? Because a tiny, seemingly insignificant rounding error at the fifth decimal place of an FX rate, well, when you multiply that across a 2 million barrel portfolio, it isn't just a quirky math error anymore. It translates to thousands of dollars of unexplained P&L loss that you're going to have to answer for. Precision here acts as a strict financial control. It ensures your data pipelines treat fractional cents with the exact same respect as millions of dollars. Let's head into Section 4, Safe Conversions and FX. Let's actually build out the pipeline and connect these governed tables to your aggregation processes.
To maintain an honest and accurate P&L across a global trading business, you have to strictly adhere to this pipeline. You can never, ever combine amounts across different units or currencies without executing a governed conversion lookup first. Think about it. If you have a trade priced in euros and another priced in US dollars, you absolutely cannot just add the raw numerical amounts together. First, you ensure the amounts carry their currency. Next, you look up a governed and dated FX rate for that specific business day. Then, you convert everything to a common reporting currency. And only then do you perform your mathematical sum for the P&L.
Section 5. The ton-barrel mix-up. I want to walk you through the anatomy of a real disaster, just to show you what actually happens in production when we ignore this discipline and take architectural shortcuts.
Imagine a cross-commodity report built by a totally well-meaning analyst. This report attempts to sum the raw quantity numbers of WTI crude, which of course trades in barrels, and imported cargoes, which trade in metric tons. What do you think happens when you add barrels and metric tons together in a SQL query, treating them as if they were identical dimensions?
Well, you get a complete catastrophe. It is literally like adding apples and spark plugs together. Because the report bypassed the unit conversion entirely and just summed up the raw numbers, the result was a total volume that was confidently presented, yet physically meaningless, and off by a massive factor. This is a classic architecture smell. The data model fundamentally failed to enforce the rule that combining across units requires a lookup-based conversion first. If governed units in a proper conversion table had been implemented, a barrels plus tons sum would be literally impossible to write by accident.
And this right here brilliantly illustrates why governed conversions matter so much across the enterprise. Just take a look at a typical data pipeline flowing from the initial trade all the way down to reporting. Notice the core principle at play here. One fact stored, that's the trade itself, but 8 distinct views are derived from it. Every single process after trade is essentially a query on that one stored fact. So if you have even a single wrong conversion factor, or maybe a skipped conversion at the reference data stage, it silently distorts absolutely everything downstream. Your position is wrong, your valuation is wrong, your P&L is completely misstated, and your final cash settlement with the counterparty, it's going to fail for sure.
Section 6, Core Takeaways and Next Steps. Let's wrap up this lesson with the absolute non-negotiables for your ETRM data models.
As ETRM practitioners, consider these 5 rules your marching orders. First off, quantity is meaningless without its unit, and that unit must be resolved through the instrument. Second, always model your units of measure and currencies as governed entities in your database, never ever as free text. Third, store your conversion factors and FX rates in dated, governed tables, not hard-coded into your reports. Fourth, use high-precision data types because, as we saw, rounding errors equal real money lost. And finally, never combine amounts across units or currencies without converting them first. If you stick to these rules, every number in your system will be rock solid, unambiguous, and perfectly accurate.
All right, so now that your trades are completely unambiguous in their quantity and currency, you need to get ready for Chapter 11. We are going to introduce the one dimension that absolutely everything else in a trading system depends on: time. We'll be separating the business date, when a thing actually happened, from the system date, which is when it was recorded in the database. I mean, how do you value a portfolio today based on data that arrived yesterday but was technically effective last week? It's a giant puzzle. Think about that, and I will see you in the next explainer.
Welcome back, everyone, to ETRM Data Engineering and Analytics from Dorga Analytics. I'm absolutely thrilled to have you here. You know, this is really the only program out there that teaches modern data engineering on a complete, real energy and commodity trading risk management platform. From the canonical trade model all the way down to a signed-off P&L, we are building it end to end, together. Now, before we jump into today's specific lesson, let's do a quick reminder of our overall course structure. This entire course is organized into 12 core modules. We start off with Module 1, Data Modeling for ETRM Systems. Then we move through 2, Reference and Master Data Management, 3, Trade Lifecycle and Instrument Modeling, 4, FPML and Trade Representation, 5, Market Data, Curves and Time Series, 6, Position and P&L Data Models, 7, Counterparty, Credit and Limit Modeling, 8, Data Lake, Warehouse and Lakehouse, 9, Event Sourcing and Audit Trail Design, 10, Streaming and Real-Time Risk, 11, Real-Time Dashboards and Analytics, and finally, Module 12, Straight-Through Processing, which is our capstone. Right now, we are deep into Module 1, and today we're tackling Chapter 11, Temporal Modeling, specifically, the critical distinction between the business date and the system date. This is a high-stakes data engineering concept that literally separates the amateurs from the true enterprise architects. So, let's get started. Here's a quick look at our agenda for today's explainer. First, we'll kick things off with a real-world disaster, the vanishing trade incident. Then, we'll briefly look at our course structure and context. Third, we'll unpack the core concept, business versus system date. Fourth, we'll explore as-of queries and history. Fifth, we'll tackle late entries and backdating. And we'll wrap it all up with enterprise architecture best practices. All right, let's dive right into Section 1. We're going to step directly onto the trading floor to examine a chaotic, real-world data problem. Imagine this scenario for a second. You're on the floor, a massive crude oil deal is agreed upon on Monday. It is live, the economic exposure is entirely real, and the desk is managing that risk. But, come Wednesday morning, the finance team reruns the official position report for Monday to double-check some numbers. And suddenly, that multi-million-dollar crude oil trade is just gone. Poof. It has completely vanished from the reproduced Monday position report. So ask yourself, how does a massive, very real deal suddenly disappear from a historical report? Well, let's look at the incident report diagnosis. The trade was agreed on Monday, right? But the trader didn't actually key it into the platform until Tuesday. The fatal flaw here, and this is a classic, painful mistake, was that the database model collapsed the business date and the system date into a single generic date column, and the system defaulted that date to the system date, which was Tuesday. So when Monday's as-of report was rerun on Wednesday, it logically filtered for all records with a date on or before Monday. Because the system only stored Tuesday, the trade was excluded, even though it was completely economically live on Monday. Make no mistake, this isn't just a tiny bug. This is a massive architectural failure. Moving right along to Section 2, let's quickly ground ourselves in the course structure and see exactly where this fits in.
As we mentioned at the top, we are currently in Module 1, which is all about foundational data modeling for ETRM systems. This module is huge. We've already covered entities, attributes, primary keys, normalization, the canonical trade entity, counterparties, books, locations, and even currencies. Now, in Chapter 11, we are adding the temporal dimension. This is the exact foundation you absolutely must have to track a canonical trade all the way to a signed-off P&L. Without this, your risk numbers will never tie out over time.
Which brings us to Section 3. Let's clearly define business versus system date. We're talking about two very distinct kinds of truth.
I want to share a quote from our curriculum that I think hits the nail on the head. The day a thing happened and the day you recorded it are different dates. Confusing them is how history gets rewritten. I want you to really let that sink in. If you are a data architect or an ETRM developer, ignoring this principle makes it completely impossible to reproduce history. You will never be able to explain to an auditor why a past report differs from a rerun today if you conflate these two timelines. So let's strip away all the complexity here. Every single fact in your trading system has two dates. First, you have the business date. Some people call this the valid date. This is when a fact is true in the real world. It's the exact moment economic exposure actually begins. Second, you have the system date, or the recorded date. This is simply when the database first learned about it. Now, most of the time, sure, they're exactly the same. But the hard, dangerous cases for risk and reporting, the ones that cause massive headaches, are when these two dates differ. Let's look at a concrete case study to see exactly how we handle those differences. Think back to our missing trade. We'll call it TRD 101001, a crude oil transaction. The trade was agreed on Monday, March 2nd, 2026. That right there is our business date. The deal is economically true, but the trader keys it in a day late, on Tuesday, March 3rd. That is our system date. A database model that stores only one date silently chooses which questions it can answer. By storing both dates as distinct, separate columns on this time-sensitive fact, we empower the business to answer both what was true and what did we know. Tracking this progression on a timeline, it becomes incredibly clear why finance often receives two entirely different Monday positions. If they ask for the position based on what was economically true on Monday, this crude deal absolutely must be included. But if they ask for the position based on what the platform had recorded by Monday, the trade must be excluded because the system didn't know about it yet. And here's the wild part. Both answers are actually correct, depending entirely on which date axis they happen to be querying. Okay, let's move to Section 4, as of queries and history. Let's see how these dates actually function in practical platform queries. Take a look at this standard ETRM as of Explorer interface. The whole point of a query like this is to reconstruct the state of the world at a chosen moment in the past. Notice how the analyst needs to toggle between the valid date, which is our business date, and the knowledge date, which is our system date. This visual proves exactly why users need to see original versus corrected P&L figures. Ambiguity about which date is meant is literally the root cause of endless, exhausting reconciliation arguments between the front office traders and the back office finance teams. So this brings us to the architect's golden rule. You never, ever allow ambiguous queries. If finance asks you for the position on the second, you don't just silently pick an access for them. In your SQL logic, you force the business to state explicitly whether they are querying based on the business date, like you see in Query 1, or the system date, like in Query 2. Exposing both and meticulously labeling every single report with its axis is how you build a mature, trustworthy enterprise platform. Now for Section 5. Let's tackle the absolute toughest temporal challenges in commodity trading platforms, late entries, and backdating. Let's say it's the 5th of the month, and someone realizes they need to correct a trade's volume, but that correction must be economically effective from the second. How on earth do we process this without breaking the system? Step 1. You absolutely do not overwrite history. Scratch that urge completely. Overwriting destroys your audit trail. Instead, step 2, you append a brand new version of the trade row into the database. Step 3, you set the business state into the past, the second, which is when it's economically effective. And finally, step 4, you set the system date to today, the 5th, which is when the platform learned of this correction. By doing this, the original version is completely preserved and your history remains 100% reproducible.
Let's wrap things up with Section 6. We're going to look at the downstream impact and cover some enterprise architecture best practices. When you apply this logic to the entire enterprise lifecycle, it's actually beautiful. You store just one fact correctly at trade capture with those distinct business and system dates. That single correct fact then cascades perfectly through all your derived views. Every box you see here after trade, whether that's enriching with reference data, applying market data curves, netting the position, calculating valuation and P&L, determining risk exposure, managing settlement cash flows, all the way to audit-ready reporting, is just a query. Because absolutely nothing is overridden and the dates are kept strictly separate, nothing downstream can silently disagree. It all ties out.
So, to summarize our enterprise best practices for all you data engineers and architects out there, keep these 5 takeaways in your back pocket. Number 1, always store business and system dates separately on time-sensitive facts. 2, force your reports to explicitly state their query access. 3, manage late entries properly by recognizing when the business date comes before the system date. 4, always append new versions on correction, never overwrite. And 5, guarantee reproducible history. Regulators and auditors absolutely demand that firms be able to reproduce a report exactly as it stood at a past date. Honestly, this is exactly why mature commercial platforms like Endure or Right Angle are temporal from the ground up. So, we've successfully separated when a thing is true from when the platform actually recorded it for a single trade transaction. But I want to leave you with this. What happens when the underlying reference data changes? What happens when a counterparty's legal name or, say, a credit limit changes over time and you need to query a past trade? That provocative little question leads us directly into our next lesson. Up next is Chapter 12, where we will take this exact temporal logic and apply it to reference data using slowly changing dimensions. Thank you so much for joining me on this deep dive, and I will see you in the next explainer.
All right, welcome back everyone to the Durga Analytics Premium Track. I am absolutely thrilled to have you here for this explainer. Look, if you are a data engineer, a data architect, a business analyst, or even a trader or risk analyst navigating the often chaotic world of energy and commodity trading systems, you are in exactly the right place. Today we're tackling a genuinely critical piece of enterprise ETRM architecture. This is one of those design patterns that literally separates the junior developers from the seasoned experts, and it is absolutely vital for regulatory compliance and accurate reporting in our industry. Just to ground us in where we are right now, we're diving deep into Chapter 12 of our course, ETRM Data Engineering and Analytics. As you know, this is the only program out there that teaches modern data engineering on a complete, real-world ETRM trading platform. We're on a journey together, taking you all the way from the initial canonical trade model to a signed-off, audit-ready P&L built end-to-end by you.
To give you the bird's eye view, the course is organized into 12 core modules. We start with data modeling for ETRM systems, then move through reference and master data management, trade lifecycle and instrument modeling, FPML and trade representation, and market data, curves, and time series. From there, we hit position and P&L data models, counterparty, credit and limit modeling, data lake and lakehouse architectures, event sourcing, streaming and real-time risk, real-time dashboards, and finally, straight-through processing as our capstone. Right now, we are wrapping up that very first module on data modeling. And before we move into the reference data management module next, we absolutely have to master how to handle reference data that changes over time. So here is our exact agenda for this explainer. First, 1. the retroactive downgrade trap. Second, 2, choosing your SCD type. Third, 3, implementing SCD type 2. Fourth, 4, the enterprise impact. And finally, 5, summary and next steps.
Okay, I really want you to internalize this quote from the course material. Rate the counterparty A today, A minus tomorrow. If you overwrite, last month's report silently lies. SCDs keep the past honest. Honestly, this is the absolute golden rule of enterprise reference data. In a regulated trading firm dealing in physical crude oil, LNG, natural gas, or power, preserving historical truth isn't just a nice-to-have. It's a non-negotiable legal and operational requirement.
Section 1. The retroactive downgrade trap, a real-world production nightmare.
Imagine you're a risk analyst or a data engineer, right? Your phone rings, and it's an auditor asking you to explain a massive, totally unexpected shift in last month's credit exposure numbers. And you're thinking, no new trades were booked. How is this possible? Let's walk through the exact timeline of this failure. Throughout March, our counterparty, let's say Mercuria, is rated A. Your ETRM system calculates all the credit exposure for your physical natural gas positions based on that A rating. Month-end closes, the reports look fantastic. But then, on April 1st, Mercuria gets downgraded to A-. On April 2nd, the auditor asks you to rerun March's month-end credit report. Because your database naively overwrote the old rating, that rerun pulls the new A- rating for all of March's historical trades. Boom! Suddenly, March's reported exposure shifts into a worse rating band entirely retroactively.
The crucial difference here lies entirely in how we handle that update. The single value override approach is a massive architecture smell. It literally destroys your historical P&L and risk reporting. You see, the report isn't failing because of bad arithmetic, it's failing because it has the wrong history. The reference data literally forgot its own past. The correct enterprise principle is the version approach. We have to version the rating so that every single value is preserved alongside the exact dates it was active. This ensures that when you rerun March's report in April, it correctly pulls the A rating that was actually in effect at that time.
Section 2. Choosing your SCD type, the architecture framework.
So, slowly changing dimensions, or SCDs, are the standard data modeling patterns we use to manage reference data that changes over time. There are 3 standard types, and as an architect, you have to choose the right one for each attribute. Type 1 keeps only the current value. It overwrites. You'd really only use this for correcting a simple typo, where the old value was flat out wrong and has zero meaningful history. Type 3 keeps only the previous value in an extra column. It's super rare and pretty limited. But Type 2, this is our champion. Type 2 keeps the full history using dated rows. It is the absolute industry standard for credit ratings, instrument specs, desk ownership, or honestly, anything else that is reported historically in an ETRM system.
Let's make this interactive. Let's frame this as a classic senior ETRM interview question. Lean in and test yourself right now. A counterparty's credit rating changes. Which SCD type do you use? Option A, Type 1, where you just store the current rating because, hey, it's simpler to query. Or Option B, Type 2, where you version it with effective dates so the history is preserved. Take a quick second to lock in your answer.
Well, if you want your system to survive production and actually pass an audit, Option B is the only acceptable answer here. SCD Type 2 is a data modeling pattern that versions rows with effective from and effective to dates. Because a credit rating directly feeds into historical credit reports, valuations, and settlements, its past values absolutely matter. Option A would just torch the history. SCD Type 2 ensures that history is preserved and 100% reproducible.
Section 3. Implementing SCD Type 2. Mechanics of the time machine.
Okay, let's roll up our sleeves. Let's look at the actual mechanics of how a developer or data engineer builds this time machine in a real commodity system database. When you create your table, let's say counterparty rating, you don't just have a counterparty ID and a rating. You add two absolutely crucial date columns, effective from and effective to. For the currently active rating, the effective to date defaults way into the future, usually December 31st, 9999. When Mercuria gets downgraded, we do not issue a SQL update command to overwrite that rating. No way. Instead, we do two things. First, we close the current row by updating its effective to date to today. Then, we insert a brand new row for the new A- rating, using today as the effective from date and 9999 as the effective to date. Seamless. No gaps, no overlaps.
Now, to retrieve that data, we use a little magic called an as-of join. When you're generating a report for a specific business date, let's say March 15th, your SQL query joins the trade table to the rating table and filters where March 15th falls greater than or equal to the effective from date and strictly less than the effective to date. This simple logic is the absolute heart of temporally correct reporting for your entire portfolio, whether you're trading crude, power, metals, or ags.
Section 4. The Enterprise Impact, from reference data to audit.
Let's zoom out and look at the macro view, because this brilliantly illustrates how this singular database decision cascades across the entire trading ecosystem. Look at this pipeline sequence: trade, to reference data, to market data, to position, to valuation, to P&L, to risk, to settlement, and finally to reporting. The trade is the one fact stored. Every single box after that is a query. It's a derived view. Reference data enriches the trade. If your reference data is overwritten, it silently poisons the market data mapping, it corrupts the valuation, it changes the P&L, and it completely invalidates the audit-ready reporting at the very end of the chain. By implementing SCD Type 2, you guarantee that all 8 of these derived views remain mathematically and historically honest.
And just to validate what you're learning today, this isn't just some theoretical academic exercise. The industry reality is that top-tier commercial ETRM platforms like Endura, Allegro, and RightAngle, they all manage their static reference data history using SCD Type 2 under the hood, exactly the way we've just discussed. Mastering this pattern makes you immediately effective and incredibly valuable when you're configuring, querying, or migrating data within these massive enterprise systems.
Section 5, Summary and Next Steps. The SCD Checklist.
Let's crystallize this into a checklist you can use on the job today. Step 1. Attribute by attribute, decide if history matters for reporting. If the answer is yes, it's Type 2. Step 2. Give your versioned rows effective from and effective to dates. Step 3. Always retrieve that data using an as-of join that filters the report date directly into the active range. And step 4, on change, insert a new row and close the previous one. Let's make this our mantra: never, ever overwrite reference data whose history matters.
All right, we've successfully made our reference data remember its past along one timeline, the valid business time. But I want to leave you with a bit of a provocative thought. What happens when an auditor needs to track not just what was technically true in the real world last month, but what we believed was true in our system at the exact millisecond a trader hit execute? That actually requires two timelines running simultaneously. And that is exactly the puzzle we're going to conquer next time in Chapter 13, Bitemporal Modeling. Thank you so much for joining me on this explainer. Keep building, keep learning, and I will see you in the next chapter.
Welcome, everyone, to this explainer. I'm your host and lead trainer, bringing you decades of hands-on experience building enterprise systems at Durga Analytics. Today, we are diving deep into Chapter 13 of our ETRM Data Engineering and Analytics course, Bitemporal Modeling. Look, if you're a data engineer, an architect, or a business analyst working in commodity trading, you already know one universal truth: data changes. But how exactly do you handle it when an auditor knocks on your door and asks what you thought your position was 3 months ago? Well, Bitemporal modeling is the absolute gold standard for audit-grade history in ETRM platforms, and today we're going to learn exactly how it answers that question. Just as a quick reminder of where we are in the grand scheme of things, this program spans 12 modules. It's the only program that takes you from a canonical trade model all the way to a signed-off P&L, built end-to-end. Right now, we're wrapping up Module 1. We've already covered everything from trade entities to slowly changing dimensions, and today we're tackling that ultimate audit-grade history model.
Here's our agenda for today's lesson. We'll be walking through the disputed valuation problem, valid versus transaction time, querying the bitemporal cell, executing backdated corrections, and finally some architectural smells and our wrap-up.
All right, let's jump right into Section 1, the disputed valuation problem.
Think about the life cycle of a modern trading system. You capture a trade. Let's say it's a massive, complex natural gas storage contract, or maybe a physical crude oil deal. From that single foundational fact, your platform enriches it with reference data, applies forward market curves, calculates your position, runs valuation, and eventually pushes it all the way to settlement. Basically, every single step after trade capture is a derived query. So, if your foundational history secretly changes out from under you, boom, everything downstream is instantly compromised. In enterprise risk, you absolutely cannot afford to have silent disagreements in your data.
Picture this happening on your trade floor. A counterparty reaches out to dispute a March 2nd valuation of a highly volatile power schedule, but they do it months later. Now here's the massive catch. Your risk team actually went in and corrected the market curve on March 5th. If your database only tracks standard valid time, your platform is only going to show the new corrected value for March 2nd. You literally cannot reconstruct what you originally reported to the counterparty. You are left completely defenseless in a $1 million P&L dispute or a regulatory audit. It's a total nightmare.
Which brings us nicely to Section 2, valid versus transaction time.
The reason that dispute turns into such a headache is because a standard single-axis timeline just can't capture both what was true in the real world and what your system believed at the time. So, we solved this by splitting time into two completely independent axes. First, you have valid time. This answers when was this fact true in the real world. If a pipeline volume was actually different yesterday, we can correct the valid time into the past. But then you have transaction time. This answers, when did our platform actually record this belief? This timeline acts as an immutable strict ledger. It is append-only. The past knowledge of your platform is never, ever overwritten.
Let's move on to Section 3, querying the bitemporal cell.
So, how do we actually ask our database what we believed in the past? Well, imagine an ETRM as-of Explorer interface. By fixing a point on both of our time axes, it's basically a time machine. On one side, you can ask, hey, what was the valuation valid on February 24th, exactly as we knew it on February 25th? And the system pulls up $72.40, your original belief. On the other side, you ask for that exact same valid date, but as we know it, today. Because a correction was recorded in March, it pulls up $72.90. By fixing both axes, solving those nasty counterpart disputes becomes completely transparent. No guesswork required.
Okay, for the developers and architects listening, let's look at the database level. Building a bitemporal fact table means upgrading your schema to include 4 very specific date boundaries. Alongside your primary keys like book ID and instrument ID, and your actual fact value like net quantity, you add your valid time range, valid from and valid to. Then you add your transaction time range, TXN from and TXN to. Now pay close attention to TXN2. Notice how it defaults to infinity? That is absolutely crucial. It signifies that this row represents our current active belief. Basically, until we physically correct it, we believe it forever.
Up next is Section 4, executing backdated corrections.
So what happens when the back office realizes a past position was just plain wrong? Listen to me closely here. We never, ever run a destructive SQL update command on the fact value. Instead, we use a graceful 2-step process. Step 1. We close out the old belief by updating that old row's TXN2 timestamp.
We change it from infinity to the current time, ending its active life. Step 2. We append the corrected belief by inserting a brand new row. We keep the valid from date safely in the past, but we set the new TXN from to right now. The magic here, both the original belief and the corrected belief safely coexist in your database forever.
Finally, we've reached Section 5, Architectural Smells and Wrap-Up.
Before you go rushing off to rewrite your entire ETRM platform to use 4 dates on every single table, we really need to talk about pragmatism. Making every table bitemporal just to be safe is a massive architectural smell. I have seen teams try to do this with UI configuration tables or minor user preferences. What happens? Storage explodes, and query complexity goes entirely through the roof. Your devs end up fighting these resource-heavy 4-date joins on data that literally no auditor will ever care about. It slows down the entire platform, and your genuinely important bitemporal tables get totally lost in the noise.
To avoid that trap, keep this bitemporal checklist handy for your enterprise architecture. First, reserve bitemporality strictly for core audit facts, your trades, your daily positions, and the reference data that drives regulated reporting. Second, always treat transaction time as append only. I can't stress that enough. Never rewrite a past belief. Third, query your data by fixing a point on both the valid and transaction axes. And lastly, leverage simpler models like standard slowly changing dimensions everywhere else. That is how you keep your trading system lightning fast and highly maintainable. So we've locked down our historical truths and successfully secured our ETRM's auditability. Fantastic. But here is the next massive hurdle. These highly normalized bitemporal tables, they are incredibly heavy to query. If a trader on the desk needs to run a complex P&L aggregation across 5 years of history, this schema is going to time out. So how do we transform this dense, audit-heavy data into a format that the business can actually analyze at lightning speed? Well, we are going to solve exactly that in Chapter 14, the dimensional model. It's going to be a great one, so I will see you in the next lesson.
Welcome to this Explainer Masterclass from Durga Analytics. We're diving straight into the foundational data modeling techniques used by the top energy and commodity trading desks in the world. I'm absolutely thrilled to have you here. Look, if you're a data engineer, a data architect, a developer, or a risk analyst working on enterprise ETRM platforms, you are exactly in the right place. Today, we're tackling an absolutely transformative concept in trading architecture, so let's get right to it. Just a quick reminder on where we are. This program, ETRM Data Engineering and Analytics, is the only one out there teaching modern data engineering on a complete, real-world trading platform. We cover 12 full modules, spanning everything from master data, trade life cycles, and market data curves, to position modeling, real-time risk, and straight-through processing. Right now, we're wrapping up Module 1, Data Modeling. Up to this point, we've built out the canonical trade model and handled complex bitemporal data. But today, in Chapter 14, we're making a massive pivot. We are shifting from a write-optimized transactional core to designing for lightning-fast analytical speed using the dimensional model. Here's our game plan for today. We'll contrast ground truth with analytical speed, define what facts and dimensions actually are, figure out how to wire them together with keys and dates, talk about the golden rule of never editing your dimensional mart, and wrap up with the key takeaways. Okay, Section 1, Course Overview in Chapter 14. It is so crucial to understand exactly where this fits into the grand scheme of your enterprise data architecture. Moving into Section 2, Truth versus Analytical Speed. For the first 13 chapters of this module, we engineered a highly normalized transactional core to safely book our trades. But now we have to face a really harsh reality about business analytics. You see, there's a fundamental tension here. The normalized core is built for ground truth. It captures complex trades flawlessly. It's exactly where a structured LNG deal or a massive crude oil cargo gets booked. It ensures we don't duplicate reference data, and it's heavily optimized for writing. But what happens when the commercial director wants to look at a risk dashboard? Well, analytics demands something entirely different. The dimensional mart is built strictly for read-optimized speed and intuitive querying.
And here is where the friction hits you. If a natural gas trader asks for a really simple cut of their P&L, let's say by desk and by month, a highly normalized database is literally going to choke. It'll require a dozen slow, complex joins just to return that one answer. Imagine trying to run a quick end-of-day exposure report for the power desk, and your query has to traverse the trade table, the instrument table, the counterparty table, the book table, and the delivery location table. It's painfully slow. It proves a tough lesson. Data that is perfectly correct isn't always data that is usable.
Section 3. Facts, Dimensions, and Slicing. To fix this massive performance bottleneck, we need a complete paradigm shift in how we shape our data. And that brings us to the bedrock of modern ETRM analytics.
What's really cool is how simple this actually is once it clicks. A fact is just a numeric measurement that the business cares about. Think daily P&L, the volumetric position of a crude oil cargo, exposure, or delta. If you can sum it, average it, or aggregate it in any way, it's a fact. In the commodity trading world, these are the hard numbers your business absolutely lives and dies by. Now, on the flip side, a dimension provides the descriptive context for those measurements. It answers the who, the what, the where, and the when. So if you're slicing that crude oil position by a specific counterparty or by a delivery point like Cushing, those are your dimensions. If facts are the numbers, dimensions are the text labels. When a risk manager says, show me our exposure to European power markets for Q3 with counterparty X, well, the European power market, Q3, and counterparty X are all dimensions. They're just the angles you use to slice the numbers. Breaking it down like this, the mapping becomes super clear. Numeric values you sum up, like daily P&L or position quantity, are facts. The labels you group them by, like the trading desk, trade date, instrument, or counterparty, are dimensions. When you sit down with a business to gather requirements, this is exactly what you need to be doing in your head. Listening to their questions, classifying the nouns into dimensions, and the amounts into facts. I want you to memorize this golden enterprise principle. Every single analytical question your traders or risk analysts ask can be decomposed into facts qualified by dimensions. Whether your front end is Power BI, Tableau, or a custom Python web app, the underlying engine expects the data in exactly this shape. When you reshape your data into numeric facts surrounded by these descriptive dimensions, that natural gas query that used to take a dozen joins, it now runs instantly with a simple group by clause. It's a total game changer. Section 4, Keys, Dates, and Connections. So, conceptually, we know what these pieces are. Now, let's talk engineering. How do we actually wire them together in a high-volume production ETRM platform?
We connect our fact tables to our dimensions using stable surrogate keys. This is absolutely critical because it elegantly handles changes over time. Think about it. If a counterparty's credit rating gets downgraded from A to B today, your historical P&L facts from last month still need to be tied to that old A rating. We use surrogate keys to point to slowly changing dimensions, or SCDs, meaning your facts are permanently linked to the specific version of reality that existed at that exact moment in time.
Then we have the date dimension, which is incredibly special. Instead of random IDs, we use meaningful integer keys, like 2026-0302 for March 2nd, 2026. Inside this dimension, we pre-compute every calendar attribute imaginable: month, quarter, is it a weekday, is it a bank holiday? We do this so your analytics dashboard never has to perform expensive date arithmetic on the fly. You absolutely don't want your BI tool trying to calculate whether a date is a business day for millions of rows in real time. By packing that logic into the date dimension, filtering out holidays becomes a lightning-fast, simple lookup. Okay, Section 5. Never edit the dimensional mart. We need to have a serious talk about architectural discipline, and I'm going to share a real-world enterprise nightmare to show you why. In any mature system, whether you're using Endure, Allegro, Right Angle, or a custom build, a single stored trade fact flows downstream into valuation, P&L, risk, and reporting. Every single downstream system is essentially a query derived from that core source of truth. This pipeline is sacred. The dimensional mart is fed by this pipeline, which means it is strictly a read-only projection of the truth.
So what happens when we break that rule? Let me tell you about the divergent dashboard incident. A well-meaning analyst notices a desk total looks wrong in a dashboard, so they go in and hand edit the dimensional mart to quote-unquote fix it, but they never apply that edit to the transactional core. Now, finance runs their end-of-month reports from the core, while the trading desk looks at their dashboard powered by the mart. The desk thinks they made $10 million, finance sees $8 million. The numbers diverge irreconcilably, no one knows which system to believe, and trust in the entire data platform evaporates overnight. It's a total disaster. The fix for this isn't technological, it's absolute operational discipline. The dimensional mart must be strictly derived from the core via your transformation pipelines. If a number is wrong, you fix the transactional core, or you fix the pipeline. Then you rebuild the mart. The mart is disposable. If it's corrupted, you blow it away and recreate it from the ground truth. You never, ever hand edit downstream data.
Section 6, Key Takeaways and Next Chapter. Let's wrap up everything we've covered today.
Here are your 5 critical takeaways as an ETRM practitioner. First, facts are the measurements you sum, dimensions are the angles you slice by. Second, your facts must reference surrogate keys to point to the correct, valid version of a slowly changing dimension. Third, always build a rich date dimension to completely eliminate query time arithmetic. Fourth, your dimensional mart is strictly derived, never hand-edit it. And finally, enterprise analytics requires this specific shape because querying a highly normalized core is just way too slow for business intelligence. Master these, and you'll bridge the gap between perfect transactional storage and wildly fast analytics.
But that leaves us with a massive architectural question. Now that we have our facts and dimensions modeled out, what exact shape should they take? Should we build a classic star schema, or should we normalize those dimensions into a snowflake schema? Both patterns exist, but choosing the wrong one for a commodity trading platform can cause serious headaches down the line. So what are the trade-offs? Think about it, and I'll see you in Chapter 15 where we dive into exactly that.
Welcome back, everyone. Today, we are putting on our Durga Analytics expert hats to tackle an absolutely make-or-break architecture choice in commodity trading platforms. This is a pivotal lesson from our ETRM Data Engineering and Analytics program, and as a quick reminder, this is the only program that teaches modern data engineering on a complete, real ETRM trading platform, from the canonical trade model all the way to a signed-off P&L, built end-to-end entirely by you. Today, we're answering a question that literally plagues every single data architecture team: star or snowflake? The choice you make right here will determine if your traders actually get real-time risk insights on a volatile natural gas book, or if they just give up, curse the system, and go right back to their manual spreadsheets.
Here's our roadmap for today's session. We're going to quickly map out the data journey, define our 2 schemas, weigh the all-important join trade-off, look at the rare times you actually should use a snowflake, walk through a real-world disaster scenario, and finally leave you with some rock-solid enterprise rules.
All right, Section 1. Let's get our bearings and pinpoint exactly where this architectural decision happens.
To set the stage, remember our overall course is organized into 12 core modules, taking you all the way from foundational ETRM data modeling and master data through trade life cycles, position, credit risk, analytics, and finally straight through processing. Right now, we are wrapping up Module 1, and we're specifically in Chapter 15. We've already hammered out primary keys, canonical trades, and bitemporal models. So now that we know exactly what our dimensions and facts are, we have to decide their physical shape before we serve them up to the business. And listen, this isn't just some academic database exercise. The choice you make in this chapter governs the performance of every single P&L and risk dashboard your trading desk will ever use. Picture a risk analyst managing a massive, highly volatile power or crude oil portfolio. When they hit refresh, they are pulling thousands of daily mark-to-market valuations, tangled up with complex market data and position snapshots. They expect that data instantly. When prices are swinging wildly, waiting 5 minutes for a query to return is just, well, it's completely unacceptable. So our goal here is twofold. Keep queries blazingly fast at massive scale, and keep the underlying SQL simple enough that your analysts don't need a PhD to query it.
Moving on to Section 2. Let's clearly define what we are actually comparing here. So what is a star schema? Basically, we deliberately flatten our data. A single-dimension row carries the product, the commodity, and the exchange all bundled together. Imagine a central trade fact table where all your actual numeric exposures and P&L live, and it radiates outward to these single, incredibly wide, denormalized tables. If you pull up a specific trade, the attached instrument dimension doesn't just give you some meaningless ID. It literally spells out natural gas and NYMX right there in the exact same row. We're optimizing the model purely for reading, completely ignoring the traditional rules of normalization, so everything a trader needs is immediately accessible.
Now, the contrast here is super interesting. Snowflake is that pure textbook normalization you learned in school, while star is the fast, redundant rebel that actually gets the job done for trading marts. You see, a snowflake absolutely hates redundancy. It normalizes dimensions out into subtables, so your instrument dimension links to a product table, which then branches to a commodity table, literally fanning out to look like a complex snowflake. And yes, sure, it saves storage space because you aren't writing the words natural gas 1,000 times, but that academic purity comes with a devastating performance tax when you apply it to a read-heavy reporting mart.
Which brings us perfectly to Section 3. Let's break down this join trade-off.
Let's ground this in reality. If a risk analyst wants to see P&L by commodity for a massive LNG book, a star schema requires 0 extra hops. The commodity name is sitting right there in the instrument row. It's just one jump from the fact table to the dimension. Done. It's incredibly fast. But in a snowflake, the database engine has to jump from the fact to the instrument, find the key in the product table, and hop again to the commodity table. When you're processing millions of daily valuation records across complex derivative portfolios, those extra joins just chew through CPU memory. You're forcing the database to do all this complex math just to piece a string of text back together.
This perfectly highlights a core Durga Analytics enterprise principle. Now, I know we spent earlier modules preaching about normalization to prevent data anomalies, but here's the secret. In a downstream read-only data mart, redundant data is perfectly safe. Why? Because it cannot drift. Traders aren't inserting new trades directly into the BI dashboard. It's being fed by your core transactional ETRM, where all that rigorous normalization already took place. Writing crude oil 1,000,000 times in your reporting layer is absolutely fine. Storage is practically free these days, but compute time, especially while a trader is yelling at you on the phone for their end-of-day risk numbers, is incredibly expensive.
All right, Section 4. When do we use a snowflake? Because as professional architects, we aren't completely dogmatic. There are exceptions.
You should only ever snowflake when you're dealing with massive, highly volatile, and widely shared hierarchies. A great example is European power trading. The geographical delivery nodes, the balancing areas, interconnectors, and grid hierarchies, they are sprawling and they change constantly. If you tried to flatten that massive shifting tree into every single dimension row, your daily ETL process would literally choke trying to overwrite millions of historical records every single time a minor grid node changed. In that very specific scenario, normalizing that delivery location into a separate table genuinely earns its extra join tax.
However, you've got to watch out for this major industry architecture smell, and that is snowflaking by reflex.
This usually happens when a data modeler, fresh out of a university database class, just normalizes everything because the textbooks say it's proper. And look, they mean well, but because of their obsession with purity, every time a desk head wants end-of-day risk, the BI tool is forced to generate a SQL query with a dozen completely unnecessary joins. The dashboard rots, it slows down to an absolute crawl, and it becomes a total nightmare for back-end developers to debug when reconciliation issues inevitably pop up.
So let's look at Section 5, the 5-join disaster, to see exactly how bad this can get in the real world.
I want you to imagine spending 6 months and a massive budget building a state-of-the-art ETRM data warehouse. You wire it up to your pristine master data, you unveil these gorgeous, slick new BI dashboards, and by Friday, the trading desk is just hitting export to CSV and doing manual VLOOKUPs on their desktops. Why? It's simple. The dashboard is timing out and traders don't wait. When markets are moving fast, they need their position data immediately, not whenever the database finally finishes crunching an overly complex query.
When we looked under the hood of this exact production incident, the diagnosis was fatal but surprisingly simple. The mart was fully snowflaked. Just to slice P&L by commodity and region, the core query had to navigate this crazy labyrinth of 5 chain dimension subtables. At the scale of millions of rows, the database engine simply choked trying to align trade capture events with market data across highly fractured tables. The fix? We just flattened those dimensions straight into a star schema. One jump from the fact table. The redundancy was totally safe, the query time dropped from minutes down to milliseconds, and the analysts finally ditched their spreadsheets for a true enterprise tool.
Let's wrap things up with Section 6, Takeaways and Next Steps. I want you to lock in this core enterprise checklist so you can take it straight back to your desk. First, star is your default for query-heavy trading marts. Second, embrace dimension redundancy. Remember, it's read-only and totally safe. Third, snowflake only for large, volatile hierarchies that truly earn that extra join tax. In your next architecture meeting, when someone inevitably pushes for data purity, you now have the ammunition to defend your star schema. Almost all commercial ETRM reporting modules and modern BI platforms are natively optimized to run lightning fast on flat star schemas. So, build for the query, not for the textbook.
Next up, we'll be diving into Chapter 16, where we tackle the math of our facts, specifically grain and semi-additive P&L metrics that just don't sum up neatly across every dimension. Until then, I leave you with this challenge. Go look at the absolute slowest dashboard on your trading floor tomorrow. Is it really slow because there's too much data, or did someone accidentally build a snowflake avalanche? Keep your queries fast, keep those dimensions flat, and I'll see you in the next lesson.
Welcome back, everyone, to the ETRM Data Engineering and Analytics program here at Durga Analytics. I'm your host, and I've spent decades working in the trenches with energy and commodity trading systems. You are tuned into the only explainer series out there that actually teaches modern data engineering on a complete, real-world commodity trading platform. Today's masterclass is an absolute must. We are diving into the mathematical heart of any trading system, making sure your numbers are actually right. Just to quickly orient us on the course map, we are currently in Module 1, which covers data modeling for ETRM systems. Out of our 20 foundational chapters in this module, we've made it to Chapter 16. Over the last 2 chapters, we successfully shaped our dimensional model and built out the data mart. But before we can move on to Chapter 17 to talk about data types and the terrifying financial cost of rounding errors, we've got to ensure our aggregations are mathematically honest. And that, my friends, is what Chapter 16 is all about. All right, here's our agenda for today's lesson. First, the exploding position bug. Second, establishing fact table graining. Third, the 3 additivity classes. Fourth, taming semi-additive facts. And fifth, enterprise implementation and takeaways.
Let's jump right into Section 1, the exploding position bug.
We're going to kick things off with a massive real-world production incident. Honestly, there is nothing that destroys a trading desk's trust in a data team faster than a glaring reporting failure. Picture this. You've got a crude oil trading book that is completely flat all month. Day in and day out, they're holding a steady, normal position of positive 8,000 barrels, right? But suddenly, your month-end risk dashboard lights up like a Christmas tree, reporting an end-of-month holding of 168,000 barrels. The desk goes into a complete panic. Risk management immediately gets involved, and your data engineering team is left scrambling to explain where on earth 160,000 phantom barrels of oil just materialized from.
So what was the culprit? It was literally just the number 21. See, there were 21 trading days in this particular month, and standard business intelligence tools, straight out of the box, just default to summing everything up. The dashboard software blindly grabbed that daily 8,000 barrel snapshot and multiplied it by 21, just stacking each day's position on top of the previous one. It had zero understanding of how to handle snapshot data across the dimension of time. For a data engineer or an architect, this isn't just a tiny glitch, it's a fundamental system-level failure in defining how measures should actually aggregate.
It reminds me of a ground truth in this business. Position does not sum across time. P&L does not average across desks. Get additivity wrong and every roll-up lies. If your dimensional model doesn't explicitly tell the visualization layer exactly how a specific measure should behave, every single rolled-up number on your dashboard is, well, confident nonsense. And this isn't just an IT headache. Millions of dollars can be completely misstated because of a lazy default aggregation, creating massive compliance and market risk issues. Moving to Section 2, Establishing Fact Table Grain. So how do we actually prevent this? To fix the dashboard, we have to go down to the absolute bedrock of our dimensional model. Before we can even dream of adding numbers together, we must define the grain. The grain is the exact, unambiguous definition of what a single row in a fact table represents. Pinning this down in one precise sentence is hands down the most important decision in dimensional design. In commodity trading, where you're juggling physical delivery points, complex pricing formulas, and financial hedges, a fuzzy green will absolutely destroy your architecture. Literally every dimension, measure, and aggregation rule flows directly from it. Let's look at an example. Take a daily P&L fact table. If we define one single row as one desk's P&L for one day, our key dimensions are explicitly date and desk. Pretty straightforward, right? But if we're modeling natural gas or LNG, and our end-of-day position grain is one book's end-of-day position in one instrument at a specific location, our keys have to reflect that exact granularity. They'd be date, book, instrument, and location. If you try to aggressively stuff trade-level detail into a daily desk-level grain, you're going to break the model, and all your resulting aggregations will be garbage. Pro tip here, this concept is so crucial that it's a staple interview question. If you find yourself in a senior ETRM, data engineering, or architecture interview, you have to be able to articulate this without missing a beat. You need to explain that without an explicit, locked-down grain, the system literally won't know which dimensions a fact can legitimately be summed across. You have to pin it down before you write even one line of SQL. Which brings us to Section 3. The 3 additivity classes. Once we know exactly what a row represents, we have to classify how the numbers inside that row behave when we start grouping them. Every measure in your ETRM system falls into one of 3 buckets. First, you have fully additive facts. These are the easy ones. They sum perfectly across every single dimension. Think total trade volume or realized P&L over a period. Second, non-additive facts. These never sum, ever. If you add 2 forward curve prices together or try to sum delta and gamma risk metrics across different underlying assets, you get mathematical nonsense. They have to be entirely recomputed or averaged based on their underlying components. Finally, the third bucket, semi-additive facts. These are incredibly tricky and are the silent killers of enterprise dashboards. They sum beautifully across some dimensions, but absolutely shatter if you try to sum them across others.
That takes us to Section 4, Taming Semi-Additive Facts.
Positions, end-of-day balances, risk exposures, they all fall into this dangerous semi-additive category, and they require a very deliberate architectural approach. So let's put on our architect hats for a second. You're tasked with rolling up daily crude oil positions for a trading desk. The risk manager asks for the monthly position, but the settlement team needs the daily flow. How do you architect that? Do you just sum all the daily snapshots over the month, or do you somehow isolate a specific point in time? Well, summing across time is a massive architectural smell. It's exactly what caused our 160,000 barrel production incident earlier. A position is just a snapshot of reality of one specific second. Adding Monday's snapshot to Tuesday's snapshot is mathematically invalid. It creates that ridiculous 21 times multiplier error and instantly nukes the data mart's credibility. Tools like Power BI or Tableau are naturally going to try to sum these snapshots out of the box, which means we, as data engineers, must handle this explicitly in the data mart layer. We cannot just cross our fingers and leave it to chance at the reporting layer. So the correct production-grade approach is to handle the time dimension completely differently than the others. We use a window function in our SQL logic, ordering by date descending to grab the most recent record. That successfully isolates the last day of the period. Basically, we take the last snapshot across time and then we sum across space, meaning we sum across our books, our instruments, and our locations. Sum across space, last across time. That is your absolute golden rule for semi-additive facts. Memorize it. Let's wrap it up with Section 5, Enterprise Implementation and Takeaways. If you get the chance to look under the hood of massive commercial platforms like Endure, Allegro, or Right Angle, you'll see this exact logic physically hard-coded right into the system. These platforms survive at a massive enterprise scale strictly because their reporting layers respect additivity. They use end-of-day batch processes and simulation tables to physically store these point-in-time snapshots in their databases. When users query the data, the system automatically aggregates balances point in time across the time dimension, while cleanly summing across the other dimensions like portfolios and legal entities. They deliberately prevent the exact dashboard error we just tore apart. They don't leave it up to chance, and neither should your custom data mart. If you remember only 5 things from today's explainer, make it these. Number 1, fix the grain first and state it in a single, precise sentence. Number 2, classify every single measure's additivity before building your rollups. Number 3, recognize that positions and P&L snapshots are strictly semi-additive. Number 4, always take the last value across time while summing across space. And number 5, remember to recompute, never sum non-additive measures like prices and complex risk ratios. Getting these foundational rules locked in is exactly what separates a junior developer from a true battle-tested ETRM architect. By applying these rules, that 21 times exploding position bug, it's never going to happen to you. Now that our aggregations are mathematically honest, we are totally ready for the next step. Join us in Chapter 17, where we're going to dive into data types, precision, and the staggering financial cost of rounding errors. Until then, take a hard look at your own systems and ask yourself, are there any silent semi-additive bugs hiding in your dashboards right now? Thanks for hanging out with me for this explainer, and keep building robust systems. Welcome back to our Expert Explainer series. I'm your host, and as an ETRM practitioner and trainer from Durga Analytics, I've spent decades deep in the weeds of energy and commodity trading systems. Today, we're zeroing in on why exact data types and rounding rules act as absolutely critical financial controls in enterprise commodity trading. Now, to a total novice, picking a data type might seem like, just a minor technical detail. But to us data engineers, architects, and risk analysts, it is literally the difference between a perfectly reconciled ledger and a multi-million-dollar headache. Just as a quick reminder, this lesson sits right in Module 1 of our comprehensive ETRM data engineering curriculum.
It's the only program that actually teaches modern data engineering on a complete, real ETRM trading platform, taking you from a canonical trade model all the way to a signed-off P&L. Right now, we're in Chapter 17 of that first module, laying down the absolute foundation before we even think about touching trade life cycles, market data curves, or real-time risk.
All right, so here is our masterclass blueprint for today. We're going to cover the ETRM course foundation, float versus exact money, precision and scale choices, the cost of early rounding, real-world penny breaks, and finally, key takeaways and next steps.
Okay, Section 1, the ETRM course foundation. Let's get right into Chapter 17. Moving to Section 2, float versus exact money, and why we absolutely have to avoid float math. Let's start with the real villain of our story here, floating point math. In general software engineering, it's super tempting to just use a standard float or double data type for numbers. It's fast, it's easy, right? But the source text we're working from today has this fantastic quote. It frames precision not as a minor technical choice, but as an absolute financial control protecting real money. A float looks completely harmless until a million-barrel notional is off by a cent times a million, then it's catastrophic. The crucial thing to understand is that a computer using a float actually cannot store many decimal values exactly. Something as simple as 0.1 becomes an approximation. So, for a weather app tracking the daily temperature, yeah, an approximation is totally fine. But for a trading book managing millions of dollars of crude oil or LNG, it's a disaster. Let's say a price is $72.40. A float might store that internally as 72.399999. Multiply that microscopic error by a massive commodity volume, sum it up across a book of thousands of trades, and suddenly your P&L is off by amounts no one can trace. The golden enterprise principle here is that money and quantities must always be exact numeric types. Section 3, precision and scale choices, where we define our exact numerics. So, once we banish floats from our money columns for good, we have to deliberately choose our exact numeric precision and scale for every single column. You define its precision, which is the total number of digits, and its scale, the number of digits strictly after the decimal point. This is a massive architecture decision because you have to match the precision to a value's downstream leverage. Think about an FX rate or a conversion factor turning a huge natural gas cargo from euros into US dollars. If you just give that rate 2 decimal places to keep it looking simple, you are injecting a massive error into the system. High leverage fields like that need the highest precision, something like numeric 20,10.
So how exactly do we allocate these digits? Well, you want to give each column enough scale for its finest value, plus what we call guard digits, based entirely on its leverage. For example, prices might need to be quoted out to 8 decimal places. Conversion factors, as we said, might need 10. But the final settlement amount, the actual hard cash changing hands between counterparties, that settles exactly to standard currency precision, which is usually just 2. Notice how prices and factors carry way more scale than that final settlement amount.
Section 4, the cost of early rounding and how we end up losing vital precision.
Now, even if you pick the perfect exact numeric types, perfectly valid numbers can still be completely ruined by bad architecture. The biggest architecture smell we see constantly in the field is rounding early and inconsistently. Why does this even happen? Usually, it's because developers want intermediate reports to look clean and pretty for human eyes, so they round a number to 2 decimal places at every single step of a multi-leg calculation. But when you do that mid-calculation, you're literally throwing away vital precision that the machine desperately needs to arrive at the correct final settlement. If we look at the SQL logic for a standard trade, let's call it TRD 1001, there is a very clear wrong way and right way to do this. The wrong way is nesting your round function inside your sum function, meaning you're rounding each individual leg of a trade first before adding them up. The proper enterprise approach is to calculate the raw quantity times the price with full exact precision, Sum all of that up and then apply your round command exactly once at the very end to produce that final settlement amount.
Section 5. Real-world penny breaks and how they cause major settlement blockages. If you don't aggressively enforce these rounding rules, you are going to hit the exact scenario operations teams dread the most. In a busy trading firm, your settlement ops depend entirely on different systems agreeing on the final number. Imagine your finance system computes a trade by rounding once at the end, but your trading system computed it by rounding each leg first. Suddenly, a multi-million-dollar settlement is completely blocked by a 3-cent break. It sounds absurd, right? But in an enterprise environment, a penny break fails automated reconciliation. Now, a human analyst has to halt their workflow, dig through thousands of trade legs, and manually hunt down phantom pennies before the money can actually move. The formal diagnosis for this disease is early rounding residue. It's a massive, recurring issue, which is exactly why top-tier commercial platforms like Endure, Allegro, and Right Angle are specifically designed to avoid it. They do this by centralizing exact decimal types and strict rounding rules within their settlement engines, carrying full precision and rounding at highly controlled points to prevent these operational nightmares. So if you're a data engineer or an ETRM developer walking into an interview, here is exactly how you map out the whiteboard solution. First, you carry the exact base quantity. Second, multiply by the exact price. Third, multiply by your high-precision FX rate. You show the exact math maintaining all of those guard digits throughout the flow. Finally, you draw a giant box at the very end labeled "round exactly once at the output." That's the winning architecture.
Section 6. Key takeaways and next steps. Let's lock in these enterprise rules. Let's wrap this up with the absolute non-negotiable rules of precision you need for your ETRM build. We've covered a lot today, going from the theoretical dangers of floats straight into the highly practical design of SQL column types and calculation logic. Just remember, precision and rounding discipline is a first-order settlement control. Floats compound into real money losses, and rounding is a decision the model must make on purpose. Never just accept a default database data type. You have to understand the specific business requirement of every single data point, whether it's a quoted power price, a daily LNG volume, or a euro to dollar conversion rate, and engineer your model to protect that data.
Now, here's a provocative question to leave you with. Your numbers are now completely exact. The math is pristine. But how do we actually enforce these rules on these precise numbers without the entire database breaking down under the pressure? Well, that brings us right to the doorstep of Chapter 18, where we are going to dive deep into constraints, referential integrity, and data contracts to completely lock down your ETRM system. We got the math right today. Next time, we make sure the structure holds up to the rigorous demands of enterprise commodity trading. I'll see you in the next explainer. Welcome back. I'm your trainer from Durga Analytics, and today we're continuing our explainer series on the ETRM Data Engineering and Analytics program. Look, this is the only program out there where you actually build a complete, real ETRM trading platform end-to-end, from the canonical trade model all the way down to a signed-off P&L. So whether you're a data engineer building high-throughput pipelines, a business analyst designing new commodity products, or a risk analyst who is just completely tired of debugging end-of-day P&L errors, you're in the right place. Because today's lesson, it is the absolute bedrock of your platform's trustworthiness. As an ETRM architect with decades of experience in energy and commodity trading, I can tell you that our entire philosophy today boils down to this one single quote. A rule enforced by the database can never be broken. A rule enforced by hope is broken the day you stop looking. I mean, I have personally seen multi-million-dollar trading errors happen simply because a team trusted their front-end UI to validate the data, but they completely forgot about the back-end integrations. So today, we're going to see exactly why we can never, ever just rely on application-level validations to keep our commodity trading data safe. Just as a super quick reminder of where we are, here's our 12-module roadmap. We're currently wrapping up Phase 1 on data modeling.
Over the last 17 chapters, we've built out this really precise, temporally sound model covering counterparties, delivery locations, bitemporal facts, the whole shebang. And today, we are diving into Chapter 18, Constraints, Referential Integrity, and Data Contracts. This is that crucial moment where we make our beautiful data model actually defend itself in production.
Here is our quick agenda for today. We'll cover rules enforced by databases, making invalid states impossible, preventing dangling relationships, validating trust, and failing fast at the source. Let's jump right in.
Section 1. Rules enforced by databases. It is time we move beyond hope and start relying on guarantees. So a data model can express business rules in one of two ways. It can either hope that every single application, every user, and every script inserts valid data, or it can configure the database itself to actively reject anything invalid. If a rule is checked only in your trade capture UI, it's literally broken the moment a manual correction script bypasses that UI. I mean, application checks are great. Actually, scratch that, they're necessary, but they only hold true where a developer actually remembered to write them. Think about a stressed-out developer running a quick database patch at 2 a.m. because an end-of-month batch process failed. If your rules live only in the application, that direct database patch circumvents all your security. Database constraints, on the other hand, give you a guarantee. They hold on every single write path forever. To see why this matters so deeply to our traders and risk analysts, let's imagine a very realistic scenario. We have an impossible negative quantity on a physical crude oil trade. Now sure, the UI blocks negative numbers, but overnight, during that 2 a.m. scramble we just talked about, a developer runs a rogue script to fix a typo and accidentally inserts negative 100,000 barrels directly into the database. Because there was no hard database constraint preventing it, the script succeeds. That impossible negative quantity sneaks past and permanently corrupts your position. Then, your end-of-day batch runs silently, double counts your risk, completely throws off your value at risk calculations, and by morning, your reported P&L is just completely destroyed. That silence is the real enemy here. Section 2. Making invalid states impossible by encoding your business invariance directly into the model. Take a look at this DDL snippet for our canonical trade table. Notice how we express our business ground truths right in the schema itself. We aren't just asking nicely for valid data, we are demanding it at the storage layer. Check out our natural gas buy and sell indicators. We're strictly constraining them using a check clause to only accept the characters B or S, no exceptions. And trade volumes? Strictly greater than 0. If an external API or a sleepy developer tries to push a negative volume, the database forcefully rejects the transaction before a commit can even happen. By systematically applying these 4 constraints, we build an unbreakable foundation. First, not null ensures we never have a missing price or volume. Second, check enforces our logic, like those strictly positive quantities. Third, unique ensures external references, like a trade ID from a clearing exchange, are never duplicated. And finally, foreign key, which is honestly so critical it gets its own section in a minute. Now, I know some developers avoid these because they're afraid of a slight performance hit during high-frequency ingestion. But let me be absolutely clear. In enterprise ETRM, the cost of corrupted data floating through your settlement system far outweighs a millisecond of write latency. Section 3. Relationships that cannot dangle. Let's talk about referential integrity. Consider this classic architect's dilemma. We have a robust relationship where a physical LNG or crude oil trade points to a specific legal counterparty. So what happens if a business analyst accidentally tries to delete a counterparty from the master data system while it's still linked to active, open trades? Well, without protection, you suddenly have ghost trades floating around your system without a legal entity attached. That is an absolute compliance nightmare for your risk management team. This code right here illustrates how the database handles that exact dilemma. Referential integrity is the unbreakable guarantee that a foreign key always points at a row that actually exists.
Without it, you get orphaned references. Your ETRM just accumulates trades pointing at deleted counterparties. And then what happens? Your data engineers are forced to write hundreds of lines of complex defensive code just so your end-of-day P&L queries don't silently drop millions of dollars in position value because an inner join failed.
But here's the catch. You have to choose your delete behavior very deliberately. We have two distinct options here. Option A is on-delete cascade. If a parent is deleted, all children are automatically deleted. This is fine for a weak entity like a cash flow, right? Because if a trade is legitimately deleted, its cash flow should disappear too. But option B is on-delete restrict. Listen, if you cascade a counterparty delete, you don't get an error. You just silently wipe out actual money-making trades from your production database. That is a massive resume-generating event. For core trade entities, you absolutely must use restrict to refuse the delete action and protect your production data.
Section 4. Trust validated, not assumed. Data contracts across boundaries.
Okay, so we've locked down our own database, but what happens when data crosses a system boundary? This is where we introduce the data contract. It extends our database discipline outside our own walls, acting as an explicit, versioned agreement about the schema, the data types, and the invariants being exchanged. So for example, if an external vendor like ICE or CME suddenly changes the format of their settlement price feeds, a data contract ensures we catch it right at the gate. We are rigorously validating trust at entry rather than blindly assuming it downstream.
Trusting cross-boundary data without a contract is a huge architecture smell. If an upstream system sends bad data and you don't check it, it flows silently into your core and eventually halts your critical end-of-day risk runs. But look at this timeline. With a contract, it's a totally different story. At millisecond 1, an upstream system sends bad data. Millisecond 2, it hits our boundary. Millisecond 3, our data contract intercepts and strictly validates it. And by millisecond 4, it's firmly rejected. We fail fast at the source, way before it has any chance to corrupt our real-time risk systems.
Section 5. Failing fast at the source. Let's pull together some actionable conclusions. So what's the big takeaway here? Whether you are working on a massive legacy Endura implementation, configuring right angle, or building a brand new in-house platform, you have to follow these 5 golden rules. 1. Encode every business invariant you can as a hard database constraint. 2. Use referential integrity so foreign keys never dangle. 3. Choose your delete behaviors wisely. Use restrict to protect trades and cascade for minor dependencies. 4. Use data contracts to validate external boundary data. And 5. Always reject bad data right at the source. This exact discipline is the only way enterprise ETRM cores remain trustworthy under heavy transactional volumes.
Now that our ETRM data is locked down, defended, and practically unbreakable, we have a new problem. What happens when the underlying commodity business changes? How do we safely evolve our architecture to capture entirely new, complex, renewable commodity types without having to run painful, system-breaking database migrations? Well, we are going to tackle that exact provocative challenge in Chapter 19. Until then, keep your constraints tight and your contracts validated. See you in the next one.
Welcome back to the ETRM Data Engineering and Analytics program. I'm your trainer from Surrogate Analytics, and today, well, we are tackling one of the absolute most critical survival skills in enterprise architecture. We're talking about how to build trade models that can actually survive real-world commodity businesses. You know, if you've spent any time working in energy and commodity trading systems, you already know that a trading desk is literally never static. Regulators are always demanding new attributes, structurers are inventing insanely complex products daily, and brand new markets can open up basically overnight. So today's explainer is all about designing your system for extension. We want to ensure that throwing in a new LNG constraint or adding a complex power block doesn't force a horribly painful system-wide migration. All right, let's dive right in.
Okay. So here's our masterclass roadmap for today. We'll start with some course context, then look at the staggering cost of core changes, break down additive versus breaking changes,
explore controlled, flexible attributes, and finally, wrap things up with some solid takeaways and next steps.
Section 1. Let's ground ourselves in exactly where we are in your journey to building a complete ETRM trading platform from scratch.
As a quick reminder, this is the only program out there that teaches modern data engineering on a complete, real ETRM trading platform, from the canonical trade model all the way to a signed-off P&L. We've got 12 comprehensive modules in total, and right now, we're at the tail end of Module 1, which is data modeling. We've already nailed down the basics, entities, normalization, the canonical trade model, temporal modeling, and constraints. Down the line, we're going to move downstream through market data, P&L, risk, and eventually our STP capstone. But here's the thing. Everything downstream completely relies on us getting the foundation right today. Specifically, we are diving deep into Chapter 19 out of 20 in this foundational module. It's called Extensibility Without Migrations. Up until now, we've built a really precise, self-defending canonical model. But actually, precision just isn't enough if it's brittle. This chapter sets the stage for how your platform is going to absorb new complexity. Think about a new crude oil assay metric, a highly structured natural gas swing deal, or maybe a new power delivery location. We need to handle all of that without rebuilding the core of your database.
Moving on to Section 2. As data architects, developers, and business analysts, let's talk about the nightmare scenario. The very real, very painful cost of rigid changes in a production ETRM system.
Picture this. It's a production incident I have personally seen play out on active trading floors, and it is not pretty. Day 1, the desk decides they want to trade a new, highly profitable structured metals product. It requires 6 unique quality attributes. Day 2, well-meaning developers try to accommodate this by running a quick alter table statement to just slap 6 new columns directly onto the core trade table. Seems harmless, right? Wrong. By week 1, deploying this triggers a massive database migration on a multi-million row table holding a decade of history. And by week 2, trading is completely frozen. You've got traders screaming on the floor because the system is locked during a volatile market event. And why did this happen? Because you just altered the core contract.
The ripple effect of a core change like that is just catastrophic. Think about it. The core trade table is a stored fact. Literally everything downstream is essentially a complex query running against that one contract. If you bolt on columns for every new European power location or agricultural grade that pops up, you are forcing a massive, incredibly risky retest. Reference data enrichment, market data curve generation, position netting, daily valuation, P&L attribution, risk exposure, settlement cash flows, all 8 of these downstream consumers are forced to just halt and verify their pipelines haven't broken. Breaking the core is ridiculously expensive.
So, on to Section 3. To prevent that massive ripple effect, we need to completely rethink how we introduce new data structures to our systems. We have to focus on extension, not alteration. If you remember literally only one thing from today's explainer, let it be this enterprise principle right here. A new product should be a new row, not a new migration. You absolutely must model for change, or else every single minor business request becomes a massive engineering project that just destroys the commercial agility of your firm.
So how do we actually pull this off? By strictly drawing a line in the sand between additive and breaking changes. Extensible design means always reaching for additive solutions. Say you need a field that only 1% of trades will ever use? Cool, add it as a new nullable column. Need a really complex new fee structure? Add a new related table. These are additive, meaning everything that worked perfectly yesterday is still going to work perfectly today. On the flip side, you must absolutely avoid breaking changes. Removing columns or adding a new required field for some niche LNG trade forces every single historical trade and every downstream system to update in lockstep. It's a recipe for disaster.
Let's look at a super practical architect's decision. Imagine a new exotic product needs 3 attributes that only it uses. Option A is to just add 3 columns to the core trade table for convenience. Option B is to add a related table keyed to the trade which holds those exotic attributes.
Option B is the one that survives in production, hands down. Option A bloats the core contract and shoves a migration onto every downstream consumer for attributes they are literally never going to query. Option B leaves the core completely untouched, protecting your P&L and risk engines from completely unnecessary downtime.
Which brings us to Section 4. What happens when variability is genuinely open-ended? In a real enterprise ETRM, especially in really complex markets like power or metals, new product types arrive constantly, and each brings a handful of unique attributes.
Now, I have to talk about the biggest architecture smell in ETRM systems, and it's a mistake I see so many novice data engineers make. I'm talking about using uncontrolled key-value dumping grounds. Essentially, just tossing a free-form JSON blob onto the trade table. Why does this rot your system from the inside out? Because every single guarantee you built, your strict data types, your referential integrity, it all just evaporates. Think about your risk analysts and quantitative developers. They cannot reliably aggregate exposure across untyped JSON. If your risk engine tries to sum up a volume field, and one trader typed in an integer while another typed in a text string, boom, the engine fails overnight. Instead, we have to use controlled, flexible attributes. We're talking about a governed catalog with strict data types, where new attributes arrive as validated data. This maintains your absolute database integrity.
When we actually translate this concept into SQL, the implementation requires some strict governance. First up, we create an attribute def table. Think of this as our catalog of allowed attributes, where we actively enforce data types like text, number, date, or Boolean. Then, we create a trade attribute table that strictly references both the specific trade and our new catalog. So now, when the desk suddenly starts trading a new agricultural product that has a unique moisture content constraint, that new attribute arrives safely as a perfectly validated data row. It is instantly usable by your reporting tools, and it's fully typed for your quants without ever needing to touch the core trade schema.
And if you're sitting there wondering, do the big players actually do it this way? The answer is a resounding, absolute yes. This additive approach is exactly how massive, long-lived commercial platforms operate in the real world. Systems like Endure, with its configurable deal model, or Allegro and RightAngle with their product configuration frameworks, they manage their product variability this exact way. They survive for decades because new products are onboarded as configuration and additive data, not as scary core migrations. Any platform that requires schema surgery for every new product simply cannot keep pace with a modern, fast-moving trading business.
All right, Section 5. Let's wrap up this masterclass with a really concrete checklist. You can literally take this straight to your next architecture meeting.
Following these 5 rules is going to ensure your platform remains agile. Number 1, treat the core trade table as an unbreakable contract. Keep it minimal and stable. Number 2, always prefer additive changes. Number 3, strictly avoid breaking changes that force pipeline-wide lockstep updates. Number 4, push that open-ended variability into a governed attribute catalog like we just talked about. And finally, number 5, never compromise your data integrity with an uncontrolled JSON dumping ground. Adhere to this checklist, and your platform can onboard a new, insanely complex commodity in a matter of hours, rather than freezing the entire business for weeks.
And that brings us to the end of Chapter 19. You've now built a correct, self-defending, and highly extensible logical model. But let's be real, a model drawn on a whiteboard isn't a database. I want to leave you with a thought. If your current architecture forces a huge migration for every single new product, are you really building a modern trading platform or just a legacy system of tomorrow? Something to think about. Anyway, now that we've protected the core, I'll see you in Chapter 20, where we are finally going to translate this beautiful logical design into physical database schemas and actual DDL. Thanks for joining me on this explainer, and as always, keep building resilient systems.
Hey everyone, and welcome. I am your ETRM trainer here at Durga Analytics, and with a few decades of energy and commodity trading systems experience under my belt, I am absolutely thrilled to welcome all you data engineers, architects, analysts, and developers to a massive milestone in our journey today. We are tackling Chapter 20 of our course, ETRM Data Engineering and Analytics. We've spent a ton of time on the design side, but today we actually make it run.
Just to ground us for a second and remind you of the big picture, this program is literally the only one in the industry that teaches modern data engineering on a complete, real ETRM trading platform. We are working through 12 major modules, everything from the trade lifecycle to market data, right through to streaming risk. Our goal is to take you from a theoretical, canonical trade model all the way to a signed-off P&L built end-to-end by you. You've already conquered the modeling basics in Module 1, so now it's time to build that physical, rock-solid foundation the rest of the enterprise is going to rely on.
Okay, let's dive into this. Here's our game plan for today. We'll start with the ETRM foundation, look at mapping the logical to the physical, actually assemble our core schema, talk about indexing for performance, and wrap it all up with some key takeaways. We're going to translate all that beautiful theoretical design work into a highly performant, executable PostgreSQL database. All right, part 1, the ETRM foundation. This is it, the grand finale of our first module on data modeling, where the previous 19 chapters finally coalesce.
There is a saying I want you to really internalize. A logical model is a promise, but physical DDL is the thing that runs. Up to this point, we've essentially been drawing architectural blueprints. We mapped out entities, normalization, temporal correctness, all crucial stuff. But a blueprint can't actually hold a trade, right? This chapter is where the design becomes concrete. This is where your database gets the ability to store a real-world commodity deal, like our ongoing example, TRD 1001.
So, moving right into part 2, logical to physical mapping. Let's look at the exact process of taking those abstract ETRM concepts and turning them into actionable, constraint-enforced database structures.
Think of your logical model as the brain of the operation. It holds our entities, relationships, and invariants. But to make that real, we need our physical data definition language, or DDL, the actual tables, foreign keys, and constraints. When we make this translation, we are going through a highly disciplined mapping process. Every single line of code you write here traces directly back to a logical decision. I can't stress this enough. Nothing physical is arbitrary in a true enterprise system. If there's a constraint in your database, it exists for one reason: a business invariant demanded it.
So how do we actually do this? Well, an entity becomes a table. Your identity becomes a primary key. An attribute becomes a typed column, and an invariant becomes a constraint. Let's talk about why this is absolutely crucial on a trading floor, specifically when turning attributes into typed columns. Numeric precision is a make-or-break physical decision. Imagine you're pricing 100,000 megawatt-hours of power, or 1,000,000 barrels of crude oil, or a massive LNG shipment. If you just default to a loose floating-point data type instead of an exact numeric precision like numeric 26 for quantity and numeric 28 for price, you're going to introduce compounding rounding errors. Fun fact, or, well, maybe not so fun for them, I've actually seen a floating-point data type error on a high-frequency gas desk literally evaporate $1 million of P&L into thin air by the end of the quarter. Precision is not optional, folks.
Right, let's hit part 3, assembling the core schema. This is where we bring all the pieces together to form the beating heart of our system. We're assembling a canonical ETRM core that maps perfectly onto the deal, instrument, and portfolio tables you'd find in major commercial platforms like Ender, Allegro, or Right Angle.
Now, as we build this schema, we absolutely do not just dump all our code into one massive chaotic script. And this brilliantly illustrates why we use ordered, dependency-aware migrations. First up, we have to create our reference data, our products, counterparties, and books. Only after that can we create our trade table. Why? Because a trade doesn't exist in a vacuum.
It has to reference valid counterparties and instruments. Finally, we generate our cash flows, which depend on the trade existing first. Getting this order right ensures perfect referential integrity.
Now, what's really interesting is how this executable SQL actually behaves in practice. We have foreign keys actively referencing the instrument and the counterparty. We have strict check constraints ensuring that the quantity is always greater than 0 and that the buy-sell flag is strictly limited to B or S. Our sample trade TRD 1001, which started as just a theoretical phone call way back in Chapter 1, is now insertable as a real constrained row of data that the entire rest of our platform can safely build on.
Okay, Part 4, Indexing for Performance. This is where things get a bit spicy. A perfectly mapped schema just isn't enough. We have to address the critical gap between a theoretically correct logical model and a production-ready database that can actually survive the sheer volume of a busy trading desk.
Picture this scenario. You've just gone live. The database is a pristine, exact match of the logical model. But suddenly, your risk analysts are complaining. The trading desk can't see their natural gas positions. Your dashboards are timing out entirely. The whole system is just unusably slow at scale. So, what physical step was skipped?
The diagnosis for this incredibly common production incident is simple but devastating. Your physical implementation faithfully mirrored the logical model, sure, but it shipped with absolutely no indexes. When your position by desk dashboard tries to join millions of trades to the organizational hierarchy, or a trader filters for a specific business date, the database is forced into doing full table scans. It's literally reading every single row over and over again while your head of trading is screaming that they're flying blind. The correctness was there, but the performance was completely forgotten.
To fix those dreaded timeouts, we have to map out our required indexes based on our actual access paths. If we're running a position by desk, we are joining on the org hierarchy, right? So we need an index on the book ID. To calculate exposure by counterparty, we need an index on counterparty ID. And for those heavy temporal as-of queries, we absolutely must index our trade date and value date. By putting these specific indexes in place, our position and P&L queries start using lightning-fast index lookups instead of system-crashing scans.
But hey, beware of the pendulum swinging too far the other way. We call this an architecture smell. Indexing nothing causes full table scans and crawling dashboards, as we just saw. But indexing everything by reflex, that creates massive problems too. Your write speeds will absolutely plummet every time a new trade is booked, and your storage costs will balloon. So the crucial takeaway here is balance. You have to balance read speeds against write costs, and you do that by measuring and only indexing the access paths your queries actually use.
And that brings us to Part 5, Takeaways and Next Steps. Let's summarize the capstone of this module and bring this intense journey through Course 01 to a satisfying close.
The industry reality is that a real ETRM go-live relies just as much on these physical performance realities, like ordered migrations, precise data types, and strategic indexing, as it does on the pristine logical design that preceded them. You literally need both to survive in production.
Let's quickly run down the 5 critical rules every data architect, developer, and analyst needs to remember. 1. Physical DDL realizes the logical design. 2. Map logically to physically with extreme discipline, nothing is arbitrary. 3. Order your schema creation by dependency to preserve integrity. 4. Index your real access paths, not every single column. And 5. Remember that this canonical core we just built is the foundation for the entire platform.
Now that Module 1 is complete, you can confidently design and defend a canonical ETRM data model and actually ship it as runnable DDL. Let's move ahead and see how this foundational core sets up our next major challenge in Module 2, reference and master data management. That's where we'll learn to govern the massive volumes of reference data that our core so heavily depends on.
I'm going to leave you with one final provocative thought. Your database is now lightning fast. It rigorously enforces all your rules, and it tracks every commodity trade flawlessly. But what happens if the master data feeding those rules, the legal entities, the product definitions, the contract templates, is completely, fundamentally wrong? Think about that for a bit, and I will see you in the next explainer where we tackle exactly that problem. Thanks for joining me today.